Voy a comprobar una vez más el sonido. ¿Por qué no me aparece?
Eso no me lo mejor. Sí, estaba por
Ya. Andreia, ¿puedes hacer la última prueba? Probando.
Hola. ¿Sí? Sí. Ya, qué bueno. Sí.
Ya. Estamos aquí porque Andreia va a rendir su examen de grado y antes de comenzar tengo que leer un acta formal, ¿ya? La voy a leer en español y luego vamos a cambiar a inglés para dar algunas instrucciones y tú puedes comenzar tu presentación. Entonces, la alumna Andreia Vanessa Rodríguez López, RUT 27.720.980-2, ha solicitado al director de doctorado de la Escuela de Ingeniería Eléctrica se le autorice rendir su examen de grado para obtener su grado de doctor en Ingeniería Eléctrica, cumpliendo con todos los requisitos mencionados en el reglamento académico. Estos son: aprobó todos los créditos del programa, obteniendo un promedio ponderado de 6,3. Desarrolló su estadía de investigación en Northeastern University, Estados Unidos, desde el 1 de septiembre del 2024 hasta el 1 de marzo de 2025. Realizó una publicación vinculada a su tesis, Coverage Prediction Models for 60 GHz Links in Urban Areas, de ella como autor principal, junto con otros coautores. Aprobó su tesis de doctorado con el tema Static Wireless Channel Modeling to Reliable Predict Indoor and Urban Coverage at Millimeter and Sub-Terahertz Waves. La comisión de este examen está integrada por el doctor Rafael Caldeiriña, profesor del Instituto de Telecomunicaciones en Leiria, Portugal; el doctor Carlos Gutiérrez, profesor de la Universidad Autónoma de San Luis Potosí, en México; y el doctor Rodrigo Carvajal, profesor de la Pontificia Universidad Católica de Valparaíso. Además, la comisión está compuesta por quien les habla, el doctor Hernán Mella, en representación del director del programa, y participaré como ministro de fe en este examen. Adicionalmente, se invita al director de tesis, doctor Mauricio Rodríguez, y ninguno de nosotros participará en la calificación final. ¿Ya? Ahora cambiamos al inglés. You will have up to 45 minutes for your PhD defense presentation, although completing it in around 50 minutes will be greatly appreciated. After the presentation, the examining committee will ask some questions related to your work, And after that, the presentation might also ask some questions, provided they hold a PhD degree. Finally, the audience will be asked to leave the room so that the examination committee can deliberate your final grade. And that is. So you can start now.
Thank you. Okay. Good morning, everybody. Thank you for being here, all of you, and who's listening. Today I'm will defend my PhD, and the title of my thesis is Statistical Wireless Channel Modeling to Reliably Predict Indoor UV Coverage at millimeters to terahertz waves. My advisor is Professor Mauricio. So let's start. This is the outline of my defense. We have an introduction. We're going to talk about the research problem, the state of art, the objectives, all the methodology, the results, conclusions, and the feature works. So, for the start, we're going to talk about for why to do this. And I mount 4 pillars for wireless communications. There we have we need to understand the propagation of the signals, and to understand this, we need measurements. In this case, some real-world measurements. And for this, after this, we can model in the channel with this in the realistic environments. For this, we can just provide the coverage, and this way we can just provide reliable coverage. This is really important in millimetric wave because we have a lot of blockage, we have diffractions, we have high frequency, so we need to understand all these challenges to improve and to deliver good networks. And this is our challenge still today, because we increase all the communication, wireless communication. So for this, in this way, I have 3 main motivations. Is the coverage with 90% signal reliability in both bandwidth and millimetric wave with terahertz. After this, I want to provide a link deployment in the realistic scenarios, and with this, a channel characterization through these statistical models. So for this, we can understand and we can answer some questions that we have, and indoor, and both indoor and outdoor environments. This is the research core. This is the core research problem that I want to answer. We have some models, but they don't reliably predict coverage with 9% probability. And at this, as the frequency is really high, we use direction antenna. So these direction antennas are research very effective against degradation. So we need to understand what is and quantify this degradation. For this, we can predict the coverage and both line of sight and line of sight scenarios. In my case, I want to analyze also corners, also indoor and outdoor environments. So this thesis address this unified both indoor and outdoor through large-scale measurements campaigns and statically robust channel modeling. So why this is so critical? Because network planning need this coverage predictions most reliably, and with 9% is really good. So for this, and in case of this, we have some errors increase with the frequency and antenna directivity. So one of these 2 models like complete each other. So it's really important to understand this. To address this, it has a lot of different study investigation this, but has different assumptions with this angular coverage and antenna behavior, and also in realistic environments. So here I can present some a basic and really major examples of a study. They're already in literature, but I want to show the lack that I want to provide the novelty of this in these scenarios. We have a characterization, but they have absence of the massive amount of data for reliably provide the coverage. The 3GPP is a standard, but they don't study an additional frequency factor between 28 and 140. And other models, they don't present some standardization of the measurements. We work with a very defined standard of our measurement. This is really important. Not only measuring for random points. We want to understand exactly what's happened with the environment. This is the indoor environment. For the outdoor, we have other different study. The difference has a lack of the diffractions and the dispersion of this environment, because this is not a confined environment. So as person around, as cars, as trees, has a lot of different obstacles. So we want to understand in 60 what happened in a street canyon in a suburban environment. So the previous study do not evaluate the need of a full angular scan, and they don't emulate a real suburban environment. They use some different highs. It's not a high with the antenna. It is on the rooftop or the rooftop of the building, or it's only a user height. So it's really important to see how this is to see, your behavior. So here I show some limitations, as I explained before. This digital channel has I don't have the laser here, has a main path loss model. I will show 9% reliability coverage. I unify this both investigation and indoor and outdoor analysis. I analyze full angular characterization, and I fully characterize direction gain degradation. So this is the lack that I want to provide, and that's the difference between my study and the previous study. To this, we mount several objective, specific one, and the general one is characterize and model the wireless channel, both indoor and outdoor, to reliably predict this coverage with a lot of monster data, with millimetric wave and sub-terahertz frames. And to this, we result in 6 specific objects, 4 in indoor, 2 in outdoor. And indoor we have 3 scenarios, in outdoor we have also 3 scenarios. This is not, it's kind of similar, but it's not the same. So I use corridors with line of sight and corridor without line of sight. And the analysis here is without line of sight, and a corridor to office with an open door, with a closed door. We want to analyze the influence of the door and this sub-terahertz and millimetric wave. And we want to analyze also if it is a frequency factor between these two bands of frequency. We want to analyze this, and we want to evaluate the effectiveness of the directional antenna. And outdoor, we also want to tunnel modeling the other suburban street canyon environments and evaluate the effectiveness of direction antennas and suburban street canyon environments. So to this, we use 3 different equipments, 2 for indoor, 28 for the 140, and outdoor 60 all of the equipments are a collaboration with Centro Tecnológico de Valparaíso and Nokia Bell Labs. And we have here some characteristics of the equipments. The most important difference between 28 and 140 and 60 is because 60 we have two antennas. This is a horn in omnidirectional antenna, so we have a results for the both antennas in 60. And this is equipment capable of measuring full angular spectra. It has up to 4 kilohertz and sampling. It's not so hard to report, so was a good equipment to measure. This is our scenarios. As I said before, 3 scenarios for indoor, 3 scenarios for outdoor. We have some nomenclature for each environment, and loss in no line of sight. And the difference are an indoor difference that we have analyzed and quantified the losses when you're around the corner, and we use 2 different distance from transmission in the corner. We want to analyze if the signal is the same when it's 1 year from the corner or is more far from the corner. And in our new one, really brand new methodology for the corridor offset is to move both antennas and the both environments, and the corridor in the office. We mount a grid-like receiver partner inside the office, and we move also the transmitter and the corridor. We want to understand if the transmitter is more far from the office, is still influence, or how much influence, and also the door influence too. And now in outdoor environments, we have two circadian type settings. In fact, we use one street, but in the both direction, a northbound and a southbound for the street. So we measure them in 10 streets in the Valparaiso here, in the other street. And basically, we put our antenna in the roof edge and offset of the roof edge, and our user was in the street. On the same street, we're gonna listen a lot of this for outdoor, the terminal same street, because the both antennas it is in the same street. And around the corner, we want to understand and quantify what's the losses when the user turn off the street corner. Here I can just talk a little bit about the measurement campaigns, how they works. As I explained before, this is not so hard. This is kind of has a little patternization, standardization about this. We just move a separation of 1 meter. We choose 2 different distances for the transmitter to a corner. We put the transmitter at different positions on the corridor, and the receiver at different positions inside the office. And for outdoor, also this was the same, but the difference was the base station was on the edge of the building, and the transmitter was in the street level. So we move from 5 every 3 meters up to 300, and after that every 5 meters. The maximum was 500 meters on the street. So we have, as I said before, 3 different scenarios, and the most difference between the scenarios it is we offset the antenna at the edge. Here I would show a lot of the real value of your individual measurements. We collect most of the 30 million of the individual points in all our environments. So it is a massive of points. And after this, we have just explain a little bit how which model we use in our characterizations. We use for the both indoor and outdoor kind of the same modeling for each environment. And indoor, we use a cross-frequency factor because we observe a little difference of observer behavior from the 28 to 140. So we saw we can just model this statistically, and we just propose a new model for outdoor when the antenna is offset from the edge. And we also have the analysis of azimuthal gain and all the indoor and outdoor environments. Our result shows, I divide my result in indoor and in outdoor. It's not so complicated to understand. So for indoor, our last result, we show that we can see, we observe the similitude of the behavior of our regression. So we found that this difference between the both was 14 dB. So we can just model this with a simple analysis of frequency. So we can model the behavior of the sign, the signal with other parameters, with other frequency to other frequency. It's basically this. I have all my parameters 28, and I can predict the behavior of the signal of 2040 and vice versa. So in indoor and with the loss, this is match really good because the error, the root mean square error was the same. There's no difference. The difference between those is 0. So we can predict was really good because the slope was the same. We also compare with the previous works in 28, and also the difference was 0.2 dB. So was really we can perform this frequency factor, and we can this cross prediction between the vote and loss. The challenge was to do this with no line of sign environment, and we tried to do this with two different models previously using in other paper for our group. So we tried the single slope scattering model, and we tried the diffraction inspired model. One was studied the scattering, and was the other one was studied the diffraction. So we just analyzed the both and 140, because in this case we don't measure the 28, which we only use the previous results of the study of our group. So we can see for the difference of the RMS error was increased only 0.7 dB. So was really respond really good, and this environment was which it was a surprise for us because we thought this is not supposed to be possible to have. So this is really interesting to see this. And also our results shows our several really low for compared to the other studies. But in corridor offset environments, this wasn't possible to do because the loss between a loss and an end loss was really high, above the 30. So this is, we cannot do this the cross reference factor here because the losses was really high. Here we also analyze the influence of the door. So we quantify what is the losses when the signal enter to the office. So in 28, it's up to 40 when the door is closed, and 34 when the door is open. And we just found that the slope is the same of free space. This is really good because we, and in this case, when you know a value of the slope, we only need to calculate the intercept. So it's really it's more easy to do. It's not so easy. So for the 140, as expected, it's more, the loss is severe than the 28. We had up to 38 dB loss when the door is closed. Also, as I explained in 140, our signal wasn't a large range of the distance, only 20 meters, and 28 we have 40 meters for the receiver in the corridor. So here we just saw a reserve larger than the other scenarios, and a curiosity was the slope for the door when the door is closed is 1.42 is the smaller slope that we have in all the indoor environments. So this is basically because the mood path inside, all the signal inside was mood path and reflections at this frequency, and fixing the slope and the no value, the model no compromise your error because it was the same basically in the both frequency. And this was the last scenario for indoor. Now I want to show this is the azimuthal gain for the indoor environments. The azimuthal gain, it is the analysis who quantify and show us what's the directive gain degradations in this environment. As we have a spinning equipment, we collected the signal from every direction, 360 degrees. So in this case, we analyze for indoor for loss. In any loss case, we have the same degradation gain. So it's really interesting to see because this kind of can prove and validated that we can use our frequency factor for cross prediction between the two frequency. So it was really interesting to see this. But for corridor opposite, this was happened because it was really different the degradation gain between these two frequency there. With 28 generate more the degradation gain than the 40, and it's really different how the signals works inside of this in this environment, and we can use this this value to analyze and how we can just improve this link deployment for this in these scenarios. So our outdoor empirical results. As I said before, we have two antennas and 60, so we have two different results. And I use the same graphics that I use in the paper because it has a lot of regressions. It would be a little messy to see, but we can understand with the table, and we can understand with the graphic only with the Omni because we can compare, and we compare with the 3GPP model. And we saw that our model, in our regression, understand better the environment than the 3GPP. Maybe for the morphology of our environments, or maybe the 3GPP model was based mostly in the simulation and ray tracing simulation, and we saw the difference between our that data and the 3GPP any loss model was 13 dB, was really high. And the empirical corner, around the corner, the results show us that we can model with two different models, the diffractions, and here we also use the dual slope, that we have a break between lossy and loss data. But as the dual slope, you have to use and you have to calculate it to different slope. We decide to use the diffraction model because it's more simple, and the difference of the result or MSA is smaller. So here we characterize both northbound and southbound street, and also we tested the parameters of one direction to predict the other direction, and the difference was not so high. It was really good that we expected. And for the last one, the last scenarios, we propose here a simple model based in the losses using knife-edge diffraction model. We previously was using a proposed model use the dual slope because we have there a break. But after more study, we saw that we can do this only with diffraction. And in the paper and in my thesis, I show all the losses and all range, and matches really good because the atmosphere was even smaller than what was found with dual slope, and really good. It really predicted the both antenna. This was a really good things to see. And here, the azimuthal gain was different than respected for indoor. Indoor is a confining environment, so we thought that indoor must be a degradation gain smaller than the outdoor. But we saw that we have a massive amount of data in outdoor. Our radar scholars is outdoor. So we saw that when the antenna is on the edge, the difference with the degradation is almost smaller than with 1 dB. So this is really good because this proved that we only have to point to the antenna, everybody will be covered. But when the user it is, and around the street corner, this is really higher than we expected. 5.8. This is the highest place, highest value. And when we just offset the antenna a little bit from the edge, this is almost 5 dB. So this proved that we need understand this degradation in this released environment, because we didn't realize this is so smaller than 1 dB when the antenna is on the edge. It's like up to 5 when this antenna is offset. And our last analysis in this outdoor, it is also really interesting because we are just thinking about beam steering, or as I said before, just fix the antenna in this one direction. And we want to understand what's the penalty of the 9% coverage. And we saw, first we analyzed all the angular spectra of the environments, all scenarios, and we just observe in the center, and 0 degrees is on the street, is along the street. We saw the signal is like 89% is from here, from there, is fluent from there. So we just say, okay, it's better fix it, or it's better to move a beam steering. And we analyze this with a simple, we choose the maximum value and the next maximum value for every scenarios. As you can see in the graphic, we have a different peaks and the 0 in the different degrees. And we just use it a simple difference about this one. And we saw if we use a fixed direction, we have a penalty of 7 dB of 9% coverage when antenna is in the edge. But when the user is in the around the street corner, is increased for 11. And when we just move the antenna, it's increased even more, 16.5 dB. So okay, it is better to use more and be steering in two best directions. The symmetry was the same, so it is our best case. But we saw that when you use more best directions, and in this case 3 best directions, we can just decrease this value. Around the corner was 8, and some streets was the minimal value was, the penalty was 13 dB. So in this case, base steering, it is the best option for if you want to cover the user when it's around the street corner, and when your antenna it's offset from the edge, it's not on the edge. Some antenna it is on the edge, but some antenna is in the center of the building. This is a real link. This is our contribution that we have in our works. We focus our group focus our investigations only in the papers. We have some little pieces of our works. Concluding, we answer our research problem. It is feasible to predict 90% probability with a lot of motion data in this band of frequency. And we just observe more interesting behavior of the signal that we don't realize it was not going to happen. We saw that the radiation gains account for this link deployment. In the corner effect, they can be modeled with a simple model, and we can quantify these losses instead of this too. And we just solve all of specific objects, and the most important one that in my opinion is in the steering case or single fixed directions. And outdoor and indoor, we can solve the influence of the door when the signal it is in the corridor and enter in the office. And with this, we have a different words opens when you finish this, because I really feel my work with Farfield is done, and I want to pass for the next level. I want to work right now with near field because I have measurements done in Boston, so I have a lot of data to process to this, and I can just we can understand. I lead to measurement campaigns in different corridors there. We have a lot of really good results to see, and I want to work with this with more passion, as I say. And I want to come back to work with subsidi systems. This is one of my first work. When I start my investigation, I work with 10 gigahertz. I want to come back to work with this. I want to see right now what's happened, penetration, angular behavior, and how we can model in these different environments. And now I want to work inside to outside and outside to inside in this frequency. I think this is the top hot topic right now in 5G. And we are done. Thank you so much.
Thanks, Andrea, for the presentation and for being kind. So we're moving on to the round of questions. Rafael, Professor Rafael,
Okay. Good morning. First of all, I'd like to thank the invitation to the faculty's examination board. For me, it's a great honor. I'm Julie, also easy, and see the great work that you guys are doing here on a very interesting topic on radio propagation in indoor and outdoor. So for me, it's a great honor. I'd like to So just to keep it short, and I have some remarks on the document on the presentation, which I like to highlight. I'd like to say that it was very nice to see you work. I appreciate the level of measurement and the effort that you put in doing the measurement on that data. And it's enormous work, huge work, and you're creating out a single model, which some of you say is good. It outperforms the 3GPP model, so that's a very strong statement. You have to be prepared for the attack. But still, I think that you try different frequencies and you pick up, I guess, two scenarios, one indoor and one outdoor. And yeah, I think it's I have all the measurement system, which I think that's very comprehensive and is appropriate for the degree and PhD. And I noticed that you have one publication published. And I think there are two or three more.
Yeah, there's two. One is under review, another group. Okay. And the other one, we try to make a small part of the offices. What? So, and the first one is the outdoor, and the next one is the indoor. It is with Nokia Group, and we want to finish some little analysis for the corridor officer for later, for a small paper one.
I think I've read in the thesis that you have already submitted that.
No, I submitted only the indoor. The indoor. Yeah. No, it's under review. Yeah, I put that as under review.
You have just one.
Yeah.
Now, well, I also
you just open the door and things changes, So can you comment? How
Yeah, of
reliable
course.
is reliable?
Of course. Here, okay, I will use this one. All this work, the indoor work is based on previous work in 28. But the previous work in 28, was made only with 1 point here and 1 point inside the office. So it's the measurement was not describe all the behavior of the signal inside. So we thought, okay, let's do this better. Let's mount a grid, apartment grid inside. And what if we close the door and open the door? So we just, but maybe you don't influence so much. And 28, maybe, but and 140, we want to understand how this works. So we just, okay, let's see what happened. And then we just saw this and 140. So wow, it's a lot of difference. Not only between loss and any loss, but with the close and open door. We saw here the difference is almost 17 degrees. So this is a lot. And my only limitation here was first the distance. Here I could measure in 20 meters, but in 28 I measured 40 meters. So I think maybe with the new equipment, because my equipment was the first equipment. This one is a spectrum analyze, and the new one equipment is more robust. It's more amplitude, so it can move more. So I think it was really good.
Can you go back to the slide we just presented, the door open and close and the impact on the door?
Yeah, of course.
We could start from there. So I'll come to this. So then you mentioned the 90% coverage. My question, why is 90% and not 95%?
Oh,
You justify 90%.
Okay.
By a meaning or because your results give you better?
no, I think 9%. It is 9%. 90%. We just thought, okay, we can just analyze the median, justify at 50%, or we can go up further, and we just saw that we'll analyze the 9%. We can just obtain the best of the two worlds. We do not to presume or over assume the value, or we can using the 99% because maybe is the best that we and network provider. So 9% was our
I'm
value.
trying to understand how you ensure that it's 90%. Something.
Okay.
So
And
what was the methodology that leads you to say it's 90%?
okay, the methodology we use is based in the azimuth game, actually, because here we choose the 10th percentile here to analyze, and then this in the cumulative probability is the 9%, not the 9th percentile. Here, the 9th percentile we use in the other analysis. So we use there this 10% and base it of this one, 9% base it of this one.
Okay, I understand now. But I understand now how you get to 90% from the CDF. Okay, so when you say the simulated full scattering,
Oh,
what does that mean? You
Yeah.
simulated that?
Yeah, we simulated for all of azimuth gain result. We simulated for scattering and both frequency. We just simulate a Rician Jesus, I just forgot the word. Distribution. Thank you. We simulated the distribution for all frequency. We already have this in mountain. We just calculated with the part of this is really, it's not so hard to do. We already have done this.
So, okay, I'm trying to understand. No, this is not a full wave ray tracing.
No.
It doesn't any. I don't want to work with on the other game because yesterday I think we had enough of that.
Yes. Thank you.
So it could be 90%, it could be 99%, it could be 90%.
Yeah.
Reading from the curve.
Yeah.
So you have the model for the curve?
Which curves?
Those curves.
I have the model for all these curves.
So you could take 90% on
Yeah,
that.
I could do I could choose 50%, I could choose 60%.
So if you take 90%, so what information do I extract from this graph?
Okay, if I took 9%,
with my unique budget, I mean.
exactly. As I want to cover 9% of the entire environment, I choose to use the 10 percentile because with this value, I can just understand the degradation gain. So if this is my degradation gain, I can understand and think, okay, with this degradation gain, I can cover 9% of my coverage, 9% of my environment. So, wow, okay, if I consider this as my system, I can cover all of this 9% user or environment.
Okay.
So
you add 3 dB in your fade margin, whatever, and you ensure with that you have 90%.
Yeah.
Probability of
this.
So let's go back to the title. And then you say static. And
static
then you say
is
open and close the door. So which
no,
one?
static is only because it's no one pass, or I don't have to deal with no one walking on my environment.
The door doesn't close by itself.
Okay, but I close the door and I go out. I open the door and I go.
So what happens between?
Nothing, because it's not collecting data. It's not our equipment, the Baltic 3 equipment, don't collect the data without we just click to collect it.
I think
okay. Do you want do you think the title would be improved?
I'm not saying the title, it's just static, you know.
Okay, you don't like the static. Okay. Okay, you did. Okay, I understand. We never thought.
Okay.
This way, but it's really good to listen.
In the outdoor scenario, this becomes even more critical.
It
then
is.
things are not static at all.
Yes, it is.
So in your geometries, you have trees.
Yeah, the trees, the cars, and buses, and people, and everything.
How do you ensure that it's not static? It could be quasi-static or something like that, but static is very strong. Okay?
Yeah, I agree with you.
So then the other question is, it seems like your model, your measurements are very sensitive to the door open and the door closed. And I believe if you move the receiver to another position, it will also be sensitive. And maybe the door open and close depends on the geometry. So if perhaps the transmitter was line of both sides of the receiver when the door was open.
No, they never gonna lose. No, they never gonna lose. I will try it here.
How can you ensure that?
Okay, here, as you can see, my distance is from the door.
Okay.
5 meters from the door, 10 meters from the door, 15, 20.
So
Here.
What do you think is the dominant?
In this case, it is reflection. All this case is reflection. All the dominant here is the reflections, and when we just send the signal here, the door is open, the entrance of the door, but the door is closed, the signal is still here, have signal here, and we can just, the door, it is the wood, it's like this one, but has a little piece of the glasses here. This is the most, like the minimal permittivity for penetration there. The signal pass for this pass for the wood because the morphology of the ambient is not this. I think the name is
But Andrea,
plywood.
you're saying it's reflection. Now you're saying it's refraction. So I'm confused now. So which mechanism is that? Is it reflection, refraction? Because the different
Okay,
things.
when the
What you're
door
trying
is
to say
open,
it
when
goes
the
through the
door is
wall.
open,
If it's through the wall, it's refraction.
I think when the door is open, it is reflections, and the door is closed, it is reflection.
But the reflection from where?
Reflection from
The wall?
the door, not the wall, the door, exactly. Because as I was seeing, the walls wasn't the plywood, the thin material is concrete.
Mm-hmm.
It's really concrete because it's our building. It's concrete. So you can see when you open the door, it's like this of the grosser of the wall.
Yeah, but are you saying that the signal doesn't propagate through the wall?
I don't believe so. I don't believe so because you saw a lot of difference when you close and you open the door.
Well, it would propagate, maybe with high attenuation. It does propagate. So you just have to quantify the attenuation.
Mm-hmm.
Okay, so I think I understood. But did you actually check that it covers the wall, or did something just to make sure the reflection is coming from the wall? Or is just the wall plus the door reflection plus?
We analyze all the angular spectrum. I don't show here, but I think I show in the pieces, in the appendix, the angular spectrum, all the patterns when all the angular received, and we saw the most high, the peak of is from the door.
The door.
So it wasn't the wall.
Okay.
Was the door.
I understand. So if you compare the ITU model, this ITU 200, whatever you model it, they actually consider the specifics, the dielectrics of all the different So there must be a reason for that, I guess, because if the wall is wood, it will reflect differently. If it was metal or another window or glass or something like that. So when you say reliably, can you compare with those models that have this fine detail?
I can try compare. I didn't notice they have one to this.
Because what you're trying to say is that your model is better than the other models.
Actually, this is the things that I want to say. I didn't say my model is better than one because I didn't compare with other model in indoor. I don't compare with nothing. I just move. I just show my regression, show my results. I don't.
It would be easy to compare.
Yeah, because all the classical shows kind of the same behavior, or the only 3GPP is kind of the same because the 3GPP is just a fancy, maybe a different free space model, so don't compare with no one.
Because I remember in the old days when we were doing coverage for Wi-Fi, they had this multi-wall, multi-floor model.
Yeah.
Which wall
I understand. I do this.
So I could have a hint what would be the signal. You take the free space and then add 20 dB per wall or 30 dB, and I have an idea.
Yeah. I remember.
I guess at those frequencies maybe you can do that, but at this high frequency, I'm a bit concerned.
This is the point, and of 140 I can compare.
I'm a bit concerned because the wavelength is very small.
Exactly.
So you're talking about 2.5 millimeter wavelength.
Yeah.
So any roughness on the surface will induce diffuse scattering. And so you may see signal, but this is the other question. How good is the signal? Because if the signal is scattered with diffuse scattering, for me it's not. It's completely depolarized. So you cannot use that for communication. So although you see signal, how good is that signal?
Exactly.
You want to comment on that?
Well, our measurements, we have noise floor. All the measurements have a noise floor. When we have the we cannot pass 20 dB of this noise floor. We always under 20 dB of this noise floor. So exactly above this noise floor. So this is our responsibility to check, because in our measurements we have the signal in real time, so we can see what's the noise floor, what is the signal. So okay, it's fine, we can measure, and we measure, and then we pass for another point. Oh, it isn't above the noise floor. It is at 20 dB, measure. So this is our.
So did you find any relation between at high frequency, 140 or something, and with the intended azimuth gain? Because I believe that if you have a highly diffuse scattering environment, that will have an impact on the.
It is, yeah. Actually, we thought that the degradation gain would be offered, or this is bad or worse than the indoor, and we saw that it is the opposite, because we have, as you can see here, we have a 3.1 of degradation gain, even when they're lost. And in confined, it is like a large waveguide. But when you have an even larger waveguide that is a strict channel, is smaller than 1 dB. So just so. Okay.
So you have this pass gain equation there, and then you say n is negative. Does it make sense?
Yes. I listened this question yesterday, and I was thinking about this, because it is fine, because as you can see here, our I understand what you say, because if it's negative, it's supposed to be in the other direction, but we are just working with path gain, and all our parameters, it is negative. So in the end, our equations still the same. Don't change it, because our intercept, it is negative, plus a negative slope, plus our mode factor, we don't use it, and then our frequency factor. So in the end, this value, it is negative, even with the plus. If it's this plus was a minus, it's not fit, because it was a sum, not a difference.
Let's take it in parts. P1 is the distance, the power at the reference distance.
Exactly.
So that's, and then you compare, and then you have, so that is dBm.
It is.
Okay. And then X.
No, in the, yeah, it's the power.
Or is it the path gain?
No, it's the power. It's the path gain in the first meter. And this here, it is our first point measurement. It's not the power. It's the path gain.
P1 is the path gain.
It's
or
path
power?
gain. Path gain.
You just said power.
No, it's the path gain, because it's this intercept.
Okay.
It's this intercept.
Okay.
It's in the dB, not in dBm.
That's correct. That's correct. You said power.
No,
that was just double checking.
No,
Now the second term.
yeah,
The second term. So you said n is negative. Nothing wrong with that. We need to maybe in a way that it is clear for us, because x is distance. Yeah.
It is.
So it seems, just looking at that, without looking at the values of n, it seems like the gain increases with the distance, which is not the case.
Yeah.
But and then to put it back to right, you say n is negative. So if you take the negative sign to inside the log, yeah, you're going to have 1 over x, and then you have 10 n log 1 over x, or minus 10 n log 1 over x. And then you look at that and say, okay, the path gain reduces with distance, and it's more intuitive for us.
Oh, okay.
There's nothing wrong with that.
Okay.
But I think what is wrong is the third term.
The third term. In this case, you will talk about the.
Or is that the random variable?
Yeah.
Is it always positive? It could be negative. So what is the
Oh.
what values?
In this case, we don't use it this one because we rotated and we just have the average of our
But what is the
measure we don't
X
consider.
or C,
This is the
sigma tells you? Is that a random variable?
Is the random
for the non-line of sight?
Non-line of sight. No, it's the one value for the shadow exactly.
For the non-line of sight path, or beyond the reference distance, yeah.
Yes.
Because normally we look at the path loss. We have the free space loss at the reference distance, and then you have the second term, but then you add in the loss. If you look at the gain, you need to subtract.
Exactly.
You need to subtract. So
exactly.
you have to
no
check
losses.
that third term. I believe it's minus, but it's
Okay.
that's I would prefer, to be honest, to see n positive, and then the x is instead of x 1 over x.
1 over x.
And then it's instead of p1, be p1 minus 10
and
no, p1 plus 10 log 10n log 1 over x.
1 over x.
And then n could be positive.
Okay.
And then you could see from the model that you increase the distance, the path gain reduces, which is what one would expect. Anyway, so I think that's okay. Now, right. So, a few other questions. I had so on slide number 5. So you see, you mentioned a lot of from literature review, the state of the art. You go from 2.55 gigahertz all the way up to 140 gigahertz. So what are you trying to show us here? I mean, is there any? Is just the trend on? Is just the extrapolation factor related to frequency, or should we be worried about propagation phenomena that exist at some frequencies and not at others?
No, in this case here, I just show like really small frequency to a higher that you can see already have a study for this. The difference is I'm going to around the corners and analyze the corridor to office. If I would just analyze the loss, was supposed to be my novelty. So I just show, look, has like a lot of study from this, different bands of frequency, but even with a lot of study of this, different frequency bands, they don't analyze two different scenarios that is really important. And I show that it is really important to analyze this. So even has a lot of study of this, it is important to understand and quantify these losses around corner, and when they open, the signal pass the corridor to office, because we already have a study that to analyze this, but in the simple way that is not really careful characterized. So I try to do this, carefully characterize this environment.
Okay. I think I understood. Now, going to slide number 8. You presented, you mentioned the indoor, outdoor scenarios, and in the outdoor scenarios, I see some trees, and I just asked before. So, now the static is no longer static.
Okay.
And my question is, how would this affect your results? So, what kind of variability should we expect from your model, from your measurements, that we should take into account?
Okay. Here you can see the effect of the woods. And here we have outdoor, is the first scenario. We have an antenna on the edge, and we have a difference from loss in any loss. And here you can see really clear that has unexpected behavior or comportment of the signal. And I just saw what I have there. It's only for the curvature of the street, because here the street is not like straight. They have some curvature here. And some directions, I think, is in the northbound. The antenna we saw, as I say, I have a photo here. The antenna has here, as you can see here, has a building here, and the street was their way. So, and only the specific distance that I saw here, I want tree there, but we don't analyze only this tree because it's only there.
Okay, so if you
One
don't,
tree.
maybe you need to look at the Fresnel clearance between the transmitter and all the measurement points along the street, just to make sure that you don't intercept that, because then maybe that variability could come from whatever. But then the model you have, if I have to use your model, I say 3 as street, rooftop, edge antenna, and then just plug in the values. But maybe you need to give some more information about the geometry, the scenario, because otherwise, maybe it's an error that someone wants to use your model just to benchmark with. Because sometimes you need to find models to benchmark, and this is a very simple model which you can easily benchmark. But maybe you need more details as to if it's you could just say if the Fresnel region is not affected, and you could say it's line of sight. So that otherwise you need to say it's quasi line of sight or it's quasi. Yeah. So it's you need to take that detailed count. Right. So on slide number 9, you mentioned 2 antennas at 60 gigahertz.
Yes.
I've seen all the measurement setups, and I can confirm it. I think this is the only one that has 2 antennas.
Yeah.
But why is this setup different from the others?
This is actually, as I said before, we have 2 like similar 28 to 60 degree equipments, and also the 28 has omnidirectional antenna as the 60, but this 140 here is only based directional, because we made this equipment, the laboratory with the other. We just design everything, printing everything, and building this from zero. So it's really like custom made from the lab, and we don't have the antenna, omnidirectional antenna to use there. The Nokia already bought one antenna, but it came with that. It's not good to use it there, so we not use it. We make the calibration. This antenna was broken, so we don't use the antenna there.
Okay. So you don't get additional information from this specific setup with respect to the other? No,
for 140, no.
So there's no point to mention 2 antennas, just for the sake of mentioning, because if you're not using it, then you say all the setups have just 1 antenna.
No, because in 60,
I was expecting something else,
No, in 60 we just show the both results, but in 28 and 140, no.
So we have the scenario with diffraction, and when you talk about diffraction, I started seeing, the diffraction equations. I go to Bertoni's book, it explains very well the diffraction, and the rate, the theory of the geometric theory of diffraction, uniform theory of diffraction, the Huygens principle, and I was trying to see if the distance to the wall for the receiver. I think you have it. I don't know what is it.
What distance? From where to where?
From the screen. So you have a diffracting screen.
Yeah.
And the distance in the horizontal from the diffracting screen to the receiver position. Normally, you have less signal as you get more in the shadow region. So I didn't see in your model you're worried about the geometry itself, the distance to the knife edge or whatever.
Yes, the losses for knife edge model
Yeah.
already do this. I explained this in the
Can you show
thesis.
the model?
No,
Okay.
actually, I don't put all the equation here. I think I don't put. Let me see. No, I just took it off. I already just showed the factor, the loss in knife edge. But in the DC, I explained exactly this. How we just calculated this loss, this influence of the distance, all the distance here, and I have two antennas, the height of the two different antennas, the height of the blockage that we have there.
But
Everything.
at 60 gigahertz, you said just use one antenna, yeah?
No, I used two.
I used to.
I show you, as you can see here, Han and Omni. Really results.
So looking at your equations,
Mhm.
looking at the domain value, your equation, you know, domain.
Discontinuity in the model.
Yeah.
Oh, we can see here as a clear grade.
In the domain, in the input domain.
Here?
In the disk.
Oh yeah, we have this different of distance here.
When x equals DC.
When equals is equal. No, but it is no, it is it is a continuous model. But they don't in our measurement x is never equal for DC. DC is the distance between the building and the our first measurement. Mm-hmm.
When it's x equals DC, what happens?
Oh.
Your model.
I think I just have to put this here, and I have to equal. We use
You have to make sure that the equation that
There is no discontinuity.
Okay, understood. Yeah, so
you have
point.
to check that. I didn't have time to compute the model,
Yeah.
but you have to make sure that
Okay.
there is no
Really,
discontinuity.
really.
So I was a bit confused. So if you go to slide 23.
23. Oh, 23.
So in that azimuth gain, something is not right in the denominator. There is some D phi.
Yeah, sorry. I
Something
just when I was passing the equations, they just moved this. It's not B.
No. It's the integral of the power over d phi, isn't it? It's not d phi over the power.
Yeah, exactly.
It's the other way around.
I think it's because this is the only way. This is the only place this is not right because here it is right.
Yeah, I saw it right.
It is right. Yeah.
Okay. I don't know how much time I have left.
I don't know either.
All the time.
Yeah.
Okay. So what time is it?
We are
Okay.
I
I have a few other questions.
in the document?
Let me see, because I have
I don't know
just
where my
give me a
document is.
second, because this I think I already mentioned before. Okay. So on equation 5, on the diffraction, I think it's slide number 13. Slide number 13. Now it seems that your model is continuous. There's no discontinuity. So it's the path gain diffraction MD.
MD what?
Oh, that's equation number 5. Can you identify equation number 5?
Okay,
Is
let's see.
PG
Question number 5.
diffraction MD.
Oh.
But it could be any of the equations because it applies to all of them. So, can you put it back? So,
No, it's happening.
yeah, okay, let's just take one of the equations. So,
Okay.
diffraction inspired model for our problem. Okay? So, let's take that one. So,
Okay.
you have 5n. Do you have?
Yes.
So, why is 5n not 6n?
Okay.
Is it magic?
No, this is one proposed model for the group. use it for street canyon, and they analyze
Which group?
the Nokia group.
Nokia group.
Yeah, exactly. It's for work that we have in 28 in outdoors, and they propose this diffraction spiral model, and they just study. In fact, this distance is important because this is the distance, the break distance when you pass to for any loss, and they analyze of this, and they suggest this is 5. It is different from the a single slope because it's still 10. It's still the same, but they saw that the slope is not so don't decay or don't decrease so slightly than 10. So they use 5.
And I believe you compared your measurement results with these models.
Yes.
And what is the error?
Oh, I saw the error here.
This one.
This one. I used single slope, the diffraction slope with error for 4.3 and 4.4, and 28 was 3.8 and 28. So it's not so distance that we have there.
So on slide 14, can you just go back one slide?
One slide.
I'm intrigued by this. Use this extrapolation factor to the frequency.
Yes.
Avoid CFF. I don't know.
Cross frequency factor.
Cross frequency. Okay. So F1 has to be greater than F2, or
F1 was what?
F1 and F2. Is there any relation between the two?
The F1 is the frequency do you have. F2 is the frequency you want to predict to, or the vice versa. I can use both. As example, F1 is 28, F2 is 140. I am in 28. I want to go to 2040. I want to predict 140. So I use 28 and 140. If I want to predict 28, it's the same. 140 to predict 28. All of this. I only use.
I mean, it's different. I mean, if you say F1 could be greater than F2, or it could be smaller than F2, then the ratio will be above 1 or below 1.
I
and
understand.
the CFF will be positive or negative. So which one? I mean,
but this is right.
So you have two frequencies.
Yeah.
So this is for the pass gain.
Yeah, it is.
So
but this is right to be positive or negative. It is right because if I have a positive here, I can go up and go up to 28. If I'm negative, actually it's the opposite. If it's positive, I can go down. If it's negative, I can go up.
So I'll give you this example here, and then you answer. You have 28, and I want to extrapolate for 140. Now let's take that easy. 28 to 56.
So 28 to 56.
Factor of 2. So what would be the CFM in this case?
Just go to minus.
The ratio between 2 is the factor. I go from 28, and I go to, let's take it 10 gigahertz to 20 gigahertz.
Okay.
So I have results for 20 gigahertz, and I want to extrapolate to 20 gigahertz, double frequency. So what should be the CFF?
Oh, it is. It is a go minus. So there will be a minus value, no?
So there is a ratio, there's a factor of 2.
Yeah.
Is it 2 or 1 over 2?
1 over 2.
So from 10 gigahertz to 20 gigahertz, it's a factor of 2.
Factor 2.
So from the physical point of view, you expect more signal or less signal?
Oh, I understand. I expect less signal.
Less signal. So the pass gain will increase or decrease?
Will increase. Path gains go up. Less signal. Increase.
You are at 10.
Yeah, no, I understand.
You want to extrapolate your results to 20. So you say that you increase the frequency, you get more attenuation.
Okay.
So the pass gain will increase or decrease?
Decrease.
Decrease. So So in this case, CFF has to be positive or negative.
In this case, supposed to be, so I want to decrease positive.
No, it has to be negative. If you have
Yeah,
a
it's
pass,
go up. Yeah,
if you
you're
have a
right.
pass gain of 100, if you double the frequency, the pass gain will be, in this case, minus 3 dB. So you have
Increase.
97
yes.
dB, because by increasing the frequency, you get more losses. So that's why I think you need to put the condition between F1 and F2.
Oh, I understand. And the condition it is the one that have to be highest, the another one. The highest is to be the
Plus minus, yeah.
plus minus. Yes, because in the
So you have to say, the starting frequency is 1, and the expected, the new frequency, the
Higher
extrapolated
than one.
frequency will be the other. And then, if you go up, it will be negative. If you go down, it will be positive.
And then you work up the sign, but the sign will come.
Oh, it come from the formula. Yeah, understood. Understood.
So it will be positive.
Uh-huh.
If the ratio is
And
positive.
yeah.
I mean,
So-
one, it will be negative.
So you put F0, that's the starting frequency, and the F1 will be the end frequency. And then
Oh, understood. Understood. Yeah. 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 From the equation it is. Yeah. Understood.
So I think you just have to revisit that. It is correct, but it depends on. I mean, from the physical point of view, I can get to that point, but then if I'm not attention, then I can do mistakes. If you go to slide 15,
Let's go then.
this is just the next one. So now you tend to go from 28 to 140 gigahertz. And you say the difference you said was something like 0.7.
About the difference because in the receiver of the ball.
But this is contradicting what you just said before, isn't it?
Oh, what?
The equation, the extrapolation factor.
No. In this case, I say it in the loss. It is feasible because the difference about the MRS error was 0, was the same MRS error, as you can see here.
Okay, so there.
Yeah.
But can you validate your extrapolating factor from those measurements?
Yes, because here, as I explained, I have my data in a 140. I have my models, okay, and I have the results of the 28 already published here. This is my comparison.
And then you extrapolate?
Yeah, then I use these parameters to predict this exactly regression
and
here.
The difference is 0.7.
Yeah, the difference of these thermometer values, the maximum is up to 0.7.
That's amazing. I mean,
I think there's a reason, but
that is amazing. But so I would be cautioned to make this very last statement because maybe if I was in the lab, I would do more measurements just to make sure there is some consistency in the result.
We try to make more measurements 28 at the same. I came here, I make all this weekend, but the equipment was not working so well. So
I just read Carol's mind, and I believe there is a reason for that. Can you explain?
And in this case here, we can saw the phenomenon here. It is this diffraction. So we just okay. So in 140 we saw the phenomenon here is diffraction when around corners. We tried two different distance, and also 28 it is the same. 28 the phenomenon there was diffraction, and we said okay, we can just compare this because in loss was the same mechanism. It was okay, we expected, but what's happening in the any loss? And when also here, the values, the 28 wasn't fixed in a freeze equation. So if there wasn't, maybe it was be okay, but whatever. And we saw this, okay, maybe it's the same mechanism, the physical mechanism and the low frequency, and we can validate this using the cross factor frequency. And we said, okay, let's try it. And we try and this put us. So basically the phenomenon there is diffraction on this corner in 3 different distance.
I think it's surprising. Because if you just have this extrapolation factor for the frequency, I feel tempted to say that at 140 gigahertz you have line of sight,
Yeah.
or at least you have wavelengths,
Mm-hmm.
and then it's just a frequency effect. And because in your simple equation model, you just take in consideration the excess loss due to the extrapolation, to the frequency change. But if it's not line of sight, then it must be reflection, diffraction, scattering, and it's still very interesting how you manage that. So maybe you have kind of a dominant path that you didn't see it, that is undermining your result. If that is, I think that needs to be checked by other
Yeah,
people.
of course. It is checking. They are checking a lot.
This has
No, this is already in the review of the group.
Yeah. I will check
that because it's amazing.
Mm-hmm. It's so amazed to be true. Okay.
That's amazing in my point of view, but I will be cautioned.
Yeah.
Don't get over excited on that, because it could not be. I mean, if it was line of sight, I would say yes.
Yeah.
So maybe there is something that I just have one last question on slide 27.
27.
And I tried to catch up the excess time yesterday.
Okay. Oh, and the last one.
The last one.
Okay.
So the first point is near field propagation. So can you tell us what kind of difficulties, or why is it different from?
Okay.
So what does near field brings into the equations, or the methodology that justifies to have a ball point in your future work?
Okay. When I was in Boston, the group there has a lot of equipment, and they work with a highly directive antennas, 1.6 HBB double the directive, so it's really high directive. This is working this, and the equipment had 20 gigahertz of bandwidth. So it's really important to see how this work. They work there with a lot of near field propagation there. They are like expert on this, but they never do a measurement like in real scenario. They have a measurement real scenario, but it was snow. Only the impact of the snow, and they don't have a measurement in a hallway. They have a lot of different hallways there. It's a curved hallway, and I arrived there. They don't work with the real measurement, and I just feel interested to work with this. And because our measurement here is narrow band, the ultra wide band they have there, and okay, here we analyze the power of the signal. There we can analyze the derivative information. We can analyze real information there. So I make almost myself the measurement.
Can I just focus on the answer?
Yeah. Okay. So it is the difference here.
It's the near field. Near field.
The difference here because we have a lot of expertise in far field. We use antennas that the far field is really small, so we can just analyze 1 meter. It is far field, so it is okay. Near field is more dedicated to work because we cannot understand very well what's happened. The gain of the antenna can change. The value we expected, it is not this value. I found all this problem there because I can use a physical base to see if my measurements is right, but in near field is uncertain. I can use it like, okay, what is this antenna is 40 dBi, the gain, what I can explain this. And then the measurement wasn't not 40, was 35. So it was changing the gain of the antenna. All this changes of this, the result I expected. So it was really interesting to see this. And I can analyze different. I can analyze the real multipath there I can analyze. Here I don't analyze the multipath. I analyze the power of the signal. There I can analyze everything that interfere of this in this environment, the multipath, all the rays they came from. We are just working to do a simulation with ray tracing for this antenna. We are just building a simulation of this antenna that we don't already have. So it's more interesting. They open a lot of things to do. So for me, I want to analyze these extra things.
Okay. Have you read the book from Bertoni?
Yeah, it is. Yeah.
It's a very nice book.
Yeah.
Yeah.
Mm-hmm.
So
I don't think I have, but
it's available out there anyway, so you can easily get access to it. Actually has some models for near field
I saw.
diffraction.
Yeah.
Because you have like a spherical incident wave,
Mm-hmm.
and the formulation changes.
Yeah.
My question, when you say near field, I'm just thinking about we need to change the formulation for the path gain for a spherical incident.
Mm-hmm.
And it is different. So when you say you have 1 meter distance, but distance from what? From the antenna, from the building? Because the building also has a far field.
Mm-hmm.
So, but what do you think in your model will change if you go from far to near field analysis? What parameters would be affected? Which new parameters have to be introduced, or we have to do completely
new parameters? I don't know, because we just working with the classical one and this don't fit. So we have to sit, because I didn't process all the data. So we cannot just say, oh, of course we have to change here, 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 here. So we don't know very well. For sure we have to add other parameters, but we don't know very well which one is this, because we don't understand which are the mechanisms of the multipath. How we can just like calculate, not calculate, but how we can explain this multipath and this equation now. So I'm not there in that point yet to understand the equation. I am understanding all the signal that I have, and then when I finish that, we're going to pass for this equations.
Let's just take a simple example, because I mean, one of the objectives of this defense is for you to have a broader knowledge and whether you can now envisage the future, because
yes.
So in the near field, I mentioned the spherical waves. We may have evanescent waves, because when you have an antenna in the very near field, in directed near field, you have modes that decay at the distance. The distance to the power of 3, and then you have modes distance to the power of 2, or to the distance of. So I guess even the Friese equation, it does not hold anymore. So going back to your model and considering that possibly the Friese equation, you have to scrap it. So maybe your model cannot be extended in as it is now for near field. We may have to start a model from scratch. So when you say research perspective, is not the application of your model for near field, or it's just
no. And in this case, I want to change everything to near field. I want to use my models in there. I want to understand all the behavior of the signal and then model the signal. If I can use the previous models, okay, but if it's not, I will not just.
So it's not an application of your model into this emerging.
I don't think so. No.
Okay, because then
it's not the point.
That explains why you go from 24 to 60 to under 40. Now you're coming back to FR3.
Yeah, I want to.
It's a big fall, isn't it?
Yeah.
So, well, is it because the other frequencies are not interested in
No,
it?
actually.
Or it's because the funding now is here?
No, as I said before, I already work with this frequency band. My graduation was in this frequency band. It was like years ago. And I worked there like many years ago, and now they are studying this. So okay, cool. I can just come back to work with this, and here I can use my models. I can use my model here for no problem. But doing this, just thinking, if years ago I worked with this, I can come back, which means my work can be used years, like after years. So I really want to come back this because in my years we only analyze the indoor environments, and I only use the log normal classic model. So I want to analyze how this how I can model it. We use a diffraction model, using the losses with knife edge models. I want to analyze this. Here I can use the FR3. I can use it in my models.
Just to complete and to finish, so I'd like you to just very quickly say what is your actually contribution?
Okay.
Out of the many contributions, pick one that you think is their contribution.
I think I have two many contributions. My work first is indoor. There we can see we can correlate it cross frequency. We can just use it even in loss case. We can just, this is a really good thing. It's a really good work to do. And the second was the beam steering. The beam steering was really good to see it, to study, because okay, we can just use a mime on there. We can just use it. It's okay, but how is the penalty? How you can quantify this? You can quantify this if you're not only using an antenna on the edge of the. Do you really need it? A mime there? Do you really need a bench there? You can only just put an antenna there and just point to the street. We want to. I think the most contribution in my work in outdoor it is quantify this penalty and to understand if in my user it is seeing my antenna. Oh no, my user not seeing my antenna. How much is my penalty? I think this is the most contribution in my work.
Well, I mean, if you have multiple beam antennas, you are being more efficiently.
Yeah.
But also you are reducing interference that comes from the multipath. So maybe you have to put that in the equation as well. And so last. Last. If I have to plan a network, what kind of recommendation? What will be the takeaway for me in terms of link budget and trade margin?
Okay.
Definition.
Let's talk about outdoor. Use it. You want to cover 9%. Use the beam steering. You can just deliver your link budget. You only have to take care of the penalty. You have to understand in your system you will be at 30 dB of the degradation and penalty to cover all your user. 60.
Okay, thank you. It's a break.
We make a short minute. Yes. Yes, sure. A break. Si fuera posible poner también el manuscrito de la tesis. Ok. Si no, se lo puedo pasar en memoria. Pero si quieren ver el manuscrito.
Obvio. Aquí tengo. No, tengo acá. No te preocupes. ¿Cómo se presenta en
We are resuming now the questions. You need the mic.
Thank you very much. So thanks a lot, Andrea, for the presentation. It was very interesting reading your document. I found it easy to read, easy to follow in general. There are some things for which I need clarification, but in general, I picked up most of the things that you presented. I'm also impressed by the amount of data that you have, the many different variations that you consider to collect your data, and I think you have done a very good job at characterizing the path loss. But there's always but as I was saying, I have
It's really hard to use this, right?
So I have questions for the sake of clarification, just for that. And I also would like to I don't know to have a deeper understanding of some of your models.
Okay.
So as I was saying without the mic, I'm gonna make this interesting because I will ask you to go back and forth between the manuscript and the presentation. So maybe we can start, with the presentation.
With the presentation?
Yeah.
Which one?
Let me tell you. Just give me 1 second. Some general comments. I'm gonna give this to you at this moment because this is our first formal interaction. Mm-hmm. So on slide 2, can you go to slide 2? Yeah. So you present this figure 1, but what is the difference between the block in green and the block in red? Because you have measurements, modeling, but the same description. So is this?
I don't believe I did. Yeah.
So it's just in general.
No, and the measurements is different from modeling because when you have the measurements, you can just collect the data in the real environment, and then with model you can characterize this real environment that you just already modeling. Was the different. I saw this like 100 times and I didn't check this.
It happens, but I'm
sorry,
gonna try
sorry.
to give you as many inputs as possible so that you got the.
And I want to comment that this is my image, so that's the reason that has no reference. This is I created, so I think I need to put that this is author.
Good. So if you're gonna use it for a publication, just fix that that issue. Then on slide 4. I will repeat myself a little bit because I think your thesis is in general well written. Also, your presentation is in general very clear. You do a good job with references, but here in particular, your first statement, that's very strong. Existing channel models do not reliably predict coverage with 90% probability.
Yeah.
Where's the reference?
That I use instead of art.
For that point.
Yeah.
And I bring this to your attention because if you go to the third and the second slide, you are very generous with references here.
Yes.
See? Yeah. So for that particular statement, a reference could make a difference. So it's also.
That's the research. I just showed the reference after this slide.
Yeah, but.
Do you think this is
it's
one of this?
Actually,
here?
This is a strong statement because I also spotted in your manuscript that you start in the introduction. I don't remember if it is in the general introduction or just in the introduction of your paper that you mentioned also that 90% of time people is indoors. And there's a reference missing there. Again.
I didn't know that.
No, there's no.
I'm so sorry, I put this in the paper. What you have. This is from an agency from the US. They saw this.
So it's good if you, for this kind of strong statements, you provide a reference.
Cool. Thank you.
And if you go to slide 8, please.
Okay.
SO3. In SO3, you wrote statistically analyze the existence of an additional frequency factor in the proposed channel models for indoor corridor environments. Good. I think I know what this means, but the point here is what is this frequency factor? How should I work with this frequency factor? Should it be a correlation factor or just an.
Exactly. This is the frequency factor that I just showed in the equations. CEFF. And we're using the equation for 20 log of frequency about other frequency.
Yes, but then this brings me to the point that you were discussing previously with Professor Rafael. I think it's good if we just go there. Can you show in these slides the model for I think it's path gain, not path loss, where you introduce the CFF.
Yes, it is.
No, there was another. I think it's the previous slide, maybe. No, there. You're right. So we were discussing the second equation from left to right. The second equation from top to bottom.
Yeah.
Right. And then you have a similar. You see, in the rest of the equations, you don't have this CFF, but in the manuscript you have, right? You have a.
In the indoor, yes, but in outdoor, no.
Okay. So I'm in this case, what is the physical meaning of that CFF? Because you're presenting this equation in log scale. This is dBs, right?
It is.
So if I have a plus minus, then that means multiplication or you're dividing, right? So the point here is it enough to have a good fitting between your prediction of the path gain? Is it enough just to multiply by the quotient of the two frequencies? Do you think that could be enough?
Well, in last case, we saw this is really fit. So we think, okay, maybe it's not need no one analysis for this. And let's pass for the end loss. This is the challenger scenario. And fix it well. So this is now what? The point here, this is a really good point. We are just think about this for the last scenario. This is even more challenging for the corridor officer. That is the losses is really high. There we have to analyze a little bit, study, because we can use this frequency factor, but not only this. We can just use it for another factor for maybe penetration, maybe other factor that professor said for the ITU wouldn't have it. So
the thing is, for you to think about, if I take this equation, the equation is nice, it's compact. I feel tempted to use it. But if I go to other equations, the fourth from top to bottom left
single
column,
slope segments, I think.
you have more parameters.
Yeah, it is.
If you want to fit a new set of data, maybe you need to bring in another parameter and another parameter, and this can grow arbitrarily. So the point here is, at some point you have to just stop and revise your model to make it better. And I was when you were just explaining a possible reason for this difference in the graphs. Can you show? I think it's slide number 12. There's no, the one where you present. I think it's path gain for different frequencies. That's for line of sight. This is non-line of sight, right?
Yeah.
So if I just add a factor, I will expect to see the same curve, but only with an offset.
Yeah, an offset in this case. No.
Yeah, and I think that's not really the case here in these figures. I'm not saying this is wrong, but I'm trying to find an explanation for this factor, and there's one key difference in your two equations. Now, go please to the other slide.
Where is the previous?
With the many equations you use.
Okay, this one.
Yeah. So, if I look at the second equation, I have the intercept E1. Then you have this other second term that accounts for the attenuation with distance, right? Or not attenuation, gain with distance in this case. But then you have capital X sigma, which you were also discussing. Shadowing. But in the other equation, in the fourth one, where's shadowing?
They not analyze in this one.
Okay.
They are not analyze in our.
And one important thing. Do you think shadowing depends on frequency? Does it change as a function of frequency?
I think so, because for the length of the signal can be really hard to propagate the signal. So if you have obstacle, all the shadowing involved there, of course, will.
Then that variable should be frequency dependent also, and that makes sense because in reality, as soon as you change your carrier, you will turn on other objects as potential reflectors, scatterers, and so on. So that's one thing I am missing in
the others,
in the slide and also in the thesis. So that's something that I should include it. If you don't need to include that, then I'd like to have an explanation. But I think we agree on this part,
exactly.
right?
No explanation, just only.
So that's one thing to consider. So next, slide 21, please.
21.
There. So this you're running a second order regression, not regression. For the fitting, you use you're not using a linear fitting, right? For the difference between your measurement data
Okay.
and and these theoretical models, these curves that you have. So I think it's a second order approximation or third order approximation.
Third order.
What?
Second.
Second order.
Yeah.
So see the cloud at the bottom, right hand.
Okay.
So you have some, I think it's green or dark points.
Wait, this one?
No, not the other one. No, at the very right. To the right. Cyan, you have some cyan and other points.
Okay.
Yeah.
Understand.
So the question is, you are fitting both the cyan and the green points, or
all
just
all of this together? We just, if you can see here,
mm-hmm.
we have this parameter. Is the corner loss parameter. Is the parameter that we have to add of our equation just to say the model how much I have to go down in this case or decrease in this case, and all this data was modeling together, even the N loss, because here the colors are different because here you can see you have I measured in the both sidewalks of the street. This represent one sidewalk, other sidewalk, one sidewalk, other sidewalk, as it respectively. So I just say for the code, where is my conditions, where is my distance, where is my corner, where it is, all this, and then do this result me. This is your M, this is your corner loss, and this is your error between your data and your model, and all this distance. This is the same. This is 3.1, 3.1, 3.1, 3.1.
I see. So it's not just a subset of your.
Only subset we have here is for the direction northbound. Actually, I did the third job all together, the both direction together, and the distance of the corners wasn't the actually the same, was different, but not too much, and we just accepted this, and then we just saw, okay, maybe it's better to separate, and then we modeled only northbound, only southbound.
Thanks for the clarification. And now on slide 18, 1.8 there. So when I read your thesis, I thought I had understood the way or your methodology to produce these curves, but today, this morning,
We didn't.
I got lost. So could you explain again? You gave already an explanation for Rafael for the scattering case, but let me tell you first what I understand, and then you tell me exactly what you did. You computed azimuth gain, as in the right is in this equation. You have traces of the power azimuth spectrum. That's what you're recording. You go to a point, you just run your sounder, and you get all these many points. So you have in azimuth a distribution of power for one recording, and you repeat that several times, and you get a set of azimuth spectra, and then you compute for each spectra. You compute this quantity, right? P max and the average power. And what I thought I was looking here was basically the distribution of these azimuth gains. Is that the?
It is because this is the all value for the azimuth gain and corridor loss for the both frequency. They come from to 9 point something to 60 point something, and also the same in 140. The we want to analyze here is the 10th percentile between the value that we have measured and one reference. What's reference here is an anechoic chamber that we don't have any, like only peak that we have there. So this is we want to analyze the the degradation, generative degradation gain.
So then my question is each curve that you're presenting specific for a distance, or is just the average of all distances?
No, it's not the average. It's all. Every point that I measure have a value of azimuth gain. One value as a per
one value.
One. This one, because here we have first we know we have a lot of spinning. We have average of the spinning, and we have only one value of path gain. And we only have one peak, one maximum, and we just put this maximum here and average all the value measure with this point. Go to another point, do the same. Go to another point, do the same. So here we will have maybe 58 points in corridor, and then we have 68 points of value of azimuth gain.
Okay. So my question is then, is this our azimuth spectrum changing with respect to the?
It is. I think I have a graph, but we don't put in the paper or in the thesis. There we have the compare the graphic, the azimuth per distance. We supposed to. I think we have this in the not in the indoor but outdoor. We have there analyze the small scaling. The small scaling we have there, so we can see exactly the azimuth gain. How is the behavior of the azimuth gain on the distance? Here we don't use it there. I can
everything.
No, we don't average everything. We just show the distribution from the minimum one to the maximum.
Yeah, but what happened with the distance? Because
here's not showing. We have this distance. We can show this. I can make a graphic to show this. Oh, this is the difference of the azimuth gain in the distance and corridor to corridor and loss. You can see this. But here, the points here show the distribution. Then you can just check the 10th percentile. You compare with the reference.
You know, it's because when I look at the equation, I mean the equation is correct, but a little more of information could help. And the power azimuth spectrum, then the way you are presenting it, and what you just taught us is depends also on the distance. So if you include distance as a variable there, maybe that will make more evident if you are taking the average also over distance, or if it's only a local average and so on. Because this is not straightforward, at least not to me, because as I've been saying, this is kind of the first time that I see this kind of statistical analysis.
Actually, azimuth gain is like a concept that was introduced for the Nokia group. They work a lot of this because our equipment is spinning, so we analyze all the degradation gain and azimuth gains and everything. So this is normal. When the people come here, okay, you can explain this very good. I don't understand very well.
But then more information in this case will be much appreciated.
Okay, I think in the paper, the both paper, we just present this a little more, explain a little well.
I checked it.
But I think it misses something because this way. We just show the distribution, but we don't show how this work and the distance. Maybe everybody wants to see this too.
I don't know if I just read the
Yeah, I understand.
But well, thank you. Then on slide no, that one's not explained. Before moving to the manuscript, what is the main or the hypothesis of your PhD? What was the
hypothesis?
hypothesis?
Okay. The hypothesis of my PhD was how much is the losses when you just turn the corners or you just turn the corners indoor or turn the corners outdoors, turn the straight corners. We want to quantify these losses. And I add there how much is the loss when the signal passed through corridor to office. And 140, the influence the door, it is great, it is higher or it is not so high like this. This was the hypothesis. How much is this losses? And then we just go through the specific to general origin.
You know, I made the question because if you make your hypothesis clear from the very outset, then it will be evident also the contribution. And I agree that this is part of your hypothesis, this explanation that you just gave me. But if I look into detail, it's rather the research question maybe. But the hypothesis should also have a potential explanation that you want to test. So what would be the explanation or the answer or your contribution to the knowledge that you want to make? I mean, this the path loss or path gain is typically like this, but because of this factor or because of this reason. And in my thesis, I demonstrate that this is true. So from that perspective, what would be the hypothesis?
Oh, in this perspective, okay, so I showed that they have a lot of studies and indoor for a lot of bands of frequency, but they don't analyze the difference, they don't analyze these losses. They just, and also don't analyze this 90% of probability coverage. And we want to quantify this for sure in our work. This was the difference. And I want to quantify this and in delivery a real value. Oh, this is the value. You can use it, network, link deployment or something. Oh, this is the value you have to consider to just start to mounting your link budget, to start mounting your link and outside and outdoor in a real realistic environment.
So the question then could be maybe if I could use your same values in a different scenario. That's not in a similar scenario, but maybe in Mexico. So there could be variations, and so I see what you have done, but I would like you to just to put it in the thesis, and also maybe that you give an explanation to make that very, very, very clear. But can we go to the manuscript? Yes. Okay. Can you go to page 4? It's the introduction. Or is C section or subsection C? A bullet or bullet? I can. A cross frequency insight. And you wrote did a comparison between 28 and 140 gigahertz revealed that higher frequency links are more sensitive to blockage and multipath. But in a sense, this was counterintuitive to me, because this means then that you have more multipath at higher frequencies.
And when you just saw in 140, we have a lot of multipath. I think in this context, the core frequency is not so good use it, but maybe in corridor of, as you saw, like first of the door.
Okay. Yeah, because you know that in the literature, the higher you, the higher the frequency, normally the more the sparser the channel. So that's the reason I found that striking. Let me go to another point. I'm just trying to focus on the important ones. So that's.
We have time. It's only 12 and 20, so we have time.
So it's chapter 3.
Chapter 3. Okay, what is the
Actually, equation 1.
Equation 1.
Mm-hmm.
Okay, let's see. Equation 1 is here.
Page number is page 12.
Let's see what.
There. Okay.
Let's come back to equation 1.
What is PR?
PR is defined as the ratio of all power collected when one spin.
And where is PR in your equation?
Yeah. Oh, you say the explanation.
I think there's a type or a mistake in the equation because you describe PR. But
PR.
PR.
Oh.
P sub R.
It's supposed
P
to
sub
be
R.
PO. Yeah, sorry.
That's a typo, right?
Yeah, it's a typo.
And then another precision that the multipath.
Okay.
You're right. Multipath fading occurs when multiple signal components are arriving through different propagation paths. Yeah. Interfere constructively or destructively
at the receiver.
You say this phenomenon associated with small scale fading
produces rough fluctuation.
But then the question is, can I have multipath associated with large scale fading?
You can.
Because
the way I describe, if you can just say it is only with the small scale.
Specific with the small scale.
I understand.
Yeah. So,
okay.
So
thank you.
There are several instances. I will hand this document to you.
No, this is just proof that you read it.
Well, as I was saying, I was interested. The more I read, I got more interested. But I found these things.
And are you gonna send me this?
Yes, I'm gonna hand this to you.
Okay.
But there are just 2 other things to discuss. Before equation 2, it's a long there. It starts on page 12. So you're right. And this is connected to Sebastian's work.
Yeah, it is.
In practice, the effective antenna pattern results from the convolution of its nominal radiation pattern with the angular power distribution of the propagation channel, also known as the scattering function. So yesterday, we had the question, is this a convolution or a product?
It's a convolution.
Really? Because you have 2 power spectra, and what would be the meaning of convolving 2 power spectra? I'll put it in the other way. Should I work with the spectral description of the system, the power azimuth spectrum, and also the power pattern of the antenna? Or if I want to speak about convolution, it is better that I just make the description based on the response of the system. You see where I'm going?
Oh, yes. Yeah, but in this case, it's not a convolution.
It should be a product. Yeah, because in principle, that's what I think. Because at the end, if I look at this from the simplest perspective, your antenna and also your channel are essentially filters.
Yeah.
You can say spatial filters.
It is.
So you can describe them from a pure system theoretic perspective as filters. And the response is not the same as the power spectrum. So one is connected to the other, but if I want to get the whole response of the system, I have to convolve the input responses. So the answer would be then it's a problem. It's the same question that you made yesterday.
So you think we have to
just
change this? Explain is not.
I think the explanation is
or...
confusing. Yeah. And also you have to check, because I am assuming that, for example, the things you are doing maybe are not exactly, I don't know, but I think that you are not convolving the spectra as such. Maybe you make your measurements. Do you have phase information in your measurements? Do you? Or just
phase?
Power?
No, only power.
So maybe this is something you should consider.
Understand.
Because, I mean, in the end, if this is correct, that you take the convolution of your measurements of power spectrum with the measurement, the anechoic chamber measurements of the antenna pattern, if you are convolving this, then at least give more arguments to make stronger, to make your case about this operation being the one that really matters here.
Understand.
Good. And okay. Some of the other questions I have in the manuscript have already been discussed, but can you go to page 12? That's the page 12. Let me see. No, it's 39 in the document.
39.
Because it's a bit confusing, because since you are presenting also the papers.
Oh, is it the paper? Okay.
I'm not sure if this is the paper.
No, this is not the paper. Just wait a minute, I think.
Yes, it's the first
this is the paper, right?
Okay.
Okay.
Next, page 12.
I will show you the papers instead. Okay. Which?
So you have equation 8.
Equation 8 is this. Okay. Oh, it is the same problem.
Yeah.
Yes, I understand.
So it's.
Why is so bad? This is not really good image.
No, but
this graphic.
In the, I think it's before the last paragraph in this page. Before that, you scroll down a little bit up.
Okay.
There. So you, in the last sentence, before the last paragraph, you have, we use 90% percentile fade depth.
Upstairs.
As the fades, yeah. As the fades of the Omni antenna did not always match classical fade statistics such as Rice, Rayleigh, and Nakagami. How did you test this the fitting?
We use all these equations tested.
And where's the
because in our code we just trying to see the fix. We just try the three: Rayleigh, Rice, and Nakagami, and all your data. We just calculate everything, and the result was which points was Rice, which points was not Rice, which points is Nakagami, which points is not, like all this. And we just saw our data was not totally Rayleigh, not about Nakagami, and more propitious to be Rice. And we just, I've spent like 4 months on this.
But then where are the results or the things that I can use?
Yeah, as you saw, the mostly was Rice, but not totally.
But you're not giving any numerical value.
No, because we here in this part, this is Mosque, we just explain, look, our data was in the distribution, not this one, as kind of 70% of this other one, and the only correlation we did there is between the the values of azimuth gain and the small scale of the omni. And we have a correlation with this one of these two values there.
Just my suggestion is that you try to be very careful with these short conclusions or short statements that are short but strong, because I left a little bit in the blue because I'm obliged to trust you. And it is not that I don't trust you, but if I know you, so I can comment and ask you, Andrea, please show me. But okay, so one last question from my side.
This was fast.
I will handle the document to you. Let me see. I'm trying to go find the conclusions. Anyway, you have future work.
Future work. In my.
You can go to your slides. Maybe it's easier.
Okay.
Yeah. So maybe you know which of your future work is going to trigger the question. Near field propagation.
Yeah.
Yeah. Also, when I read this deviates significantly from your thesis. So one thing, just my reasoning is that you already spent a lot of time working on a topic. It doesn't mean that you have to stick there forever, but also you have a lot of results, and based on the outcome of this evaluation, there are still many things to show and to analyze. So it makes sense, at least, to include here one point that considers a refinement. Yeah.
Okay, my answer to this is that I want to pass this to another person who is also doing PhD in this area. I want to she can maybe solve and respond this other question they have been in this, and could this will be her PhD. So for me, really I want to pass for this new one, totally new one, and maybe she can just find another analysis, find another results, or refine what I did. This is really good. She already doing measurements with 140 was really cool and great. So for me myself, I want to pass to another one. I want to dedicate myself to new things. So as I dedicated myself for my PhD for this investigation, I want to dedicate 100% for two of this or only one of this.
That's valid. I mean, you can do that, but it's also something to consider that maybe you can not dedicate full time to this to the extension of this work, but you can be involved and try to make a more solid contribution, in the sense that all of these aspects that are kind of weak, let's call it weak, you can just be 100% sure that it is like what I'm saying is exactly true, because I have this evidence. But that's again, that if you want to move to other things. But the question is, here in the thesis and also in the presentation, you mentioned near field, but this is a very challenging research problem, and the way you presented is very the word I would use is simplistic, because I don't have any indication here. You've already done some measurements that you explained that, but I cannot tell based on this.
Oh, I understand. So okay.
And I would like to know exactly what Rafael asked you. Are you working with in the reactive near field region or in the radiating near field region? How are you going to use the concepts? Because we were talking about you were talking about the free-space model. How is it going to change? But I have another question. How are you going to compute the power? is it going to be a real quantity? Could it be an imaginary quantity? Power or not?
No, in this case, we're using specific equipment that we created our signal, and then we transmit it, and then we demolated the signal and check if it's the same. So it's kind of as a word I can use it. It's kind of a well-known work, but in this simple case. So I know what I'm sending, and when I receive it, I demolate this. I saw, okay, I sent this. I sent the exactly signal, and now I want to see what is happening between. Because and in this case, I didn't explain this. I didn't know that I have to explain exactly what I want to do, because was only a 6-month internship. There's a lot of work. I still processing the data, and the problem, or it's not my problem, the challenge we faced it there, as I don't know what to compare the result that I have. We just analyzed all the multipath, we analyzed for the liquefy, we analyzed everything, everything different that I didn't analyze here. In all my work, I analyze power. I didn't analyze, just using a narrow band. There is a ultra wide band. I have 20 gigahertz of bandwidth I can use. So it's a real new work to work, and really exactly to what to. So.
But the point here is that in fact some of the questions that we are making here are not only related to your thesis, because one of the things we'd like to know is that you have the vision that is expected from a PhD, because at the beginning when you started, maybe you had a more naive vision of things, and now you see more things. You see more things.
Yeah.
And if you just present near field channel characterization as a topic for your future career, then I want to know if you have at least this kind of you are aware of the challenges you are facing, of the problems you are facing. And here I cannot see that.
And how much I am into in this topic. Okay.
Because I could ask you, for example, if we already discussed these two popular regions in your field, but can I say that there will be electromagnetic waves everywhere in space, far field, radiating near field, and also reactive field? Do we have electromagnetic waves in all space or not?
In space, I don't know. They use it in indoor.
Okay, I mean your antenna.
The group already do this research group for space. They are doing exactly equipment.
I mean space. I mean
sorry,
the
environment.
Yes, the spatial dimension. And let me just framing better my question. This electromagnetic field that you are radiating with your antenna, does it behave as a wave everywhere in space or not? Have you thought about that?
You say what?
The electromagnetic field that you radiate with your antenna. It radiates an electromagnetic wave. That's what we use at least in far field. But can we say that the field will behave as a wave all over through space or not?
No, with this type of measurement, they don't. They just like really confine of the lobe of the antenna, and we have to also the antenna is similar as info antennas, and it's really hard to analyze of this. This is the problem that I do right now, because I not just point of the antenna each other. I move the antenna a range of angles to analyze everything. So it's really different for the preliminary results. And we thought it's like this is not right, let's revise again, and we revise again.
So one suggestion I have is that it is good that you're looking for these new challenges, but try also to go a little bit beyond just the experimental research. Try to complement this with a solid theoretical foundation, because that way you will find some ways to apply for successful measurement campaigns, successful analysis, and as I was saying, you will always learn something if you are open to dig into the theory. So consider the book. I will get a copy for myself. Bertoni.
Bertoni, I already have it. I don't remember if it's already pressed or is a PDF, but I have it. It's like the one of the first book the professor just sent me to read to understand this.
And just as a quasi-final remark, I found in your manuscript that you talk in several parts about presenting comprehensive characterization of the wireless channel in general. But this can be taken as an overstatement because you're just focusing on path loss or path gain or the azimuth gain, but this is not the complete channel.
Oh, I understand.
So, and if I just read the paper saying that it's giving a comprehensive description of the channel, I would expect distribution of fades, also temporal dynamics, correlation functions, also these spectral functions, coherence time, coherence bandwidth, stationarity distance, and so on. So that's comprehensive. So try just to put things into the proper perspective. And
thank you.
Yeah, this is narrow one, correct? And just to wrap up, do we know the status of the papers that you have on the review?
No.
It's still on the review.
I'm on the label, yeah. It's still on the review. They don't say nothing. I just check every day. They don't.
Okay, good. So I think I will finalize with this because otherwise. Thank you very much.
Thank you. Good afternoon.
Good afternoon.
I second my colleagues with congratulations. Interesting work, absolutely. I still have some questions, so if you go to slide 3, please. Yeah. It says the first thing that came to my mind is why do you want reliable statistical models? Why other models are unreliable? What do you understand by reliable?
Well, we're not saying this the other model wasn't reliable or unreliable. We just want to like determine or affirm this is 90%. And if you have 90% of the coverage, supposed to be you can rely with this. I think it's only a way to say because in the group is really common to say this.
Okay, but my question is, if the word was reliable or accurate? I don't know. That came to my mind whenever especially the title of your thesis, reliability. I'm not sure if that's.
It was like the keyword there.
Yeah, and I'm not sure if that's the correct word or not. Something to think about. Then on the next slide, you said that your existing channel models do not reliably predict coverage with 90% of probability. What I don't understand, because I don't get all the information from what you mentioned here, is that because they have another percentage of probability, or they just don't deal with that?
They don't say nothing about probability. They just show the categorization. They don't analyze if it's the coverage of 10, 70, or 9%.
Okay, so how do you find that 90% of coverage?
Again, we just analyze based on the azimuthal gain, as I said before. We just check the 10 percentile between the azimuthal gain, is degradation gain, and the reference, and then we just saw, okay, this is the 10 percentile, so above of this is 9%, so we can just assume this is our 9% of coverage. This all this points is 9%.
Okay. If you go to the next slide, please.
Oh, sorry.
No, actually, sorry. Right. Is it that you compare your work with this state of the art? There exists a characterization of myelin channels in 2.55 and 24 gigahertz around corners of hallways. That's what they analyze. And then you mentioned that there's an absence of statistical models with massive amounts of data using directive antennas at 28 and 140 gigahertz. Is that a fair comparison?
It is, because in this case we just not compare the frequency. We are just compare the scenario.
Okay.
The scenario they use is kind of really similar to ours, but only analyze a few points here. Look, it's only 4 points in the corner. They use also 2 corners, but it's 4 points only. It's a minimal, small number of points.
Okay, but then your comment is misleading because you mentioned the frequencies. You say that there's a lack of statistical models at those frequencies, and those frequencies are not analyzed in the reference that you mentioned. So that I think that the comment would just be there is an absence of statistical models.
No, the
the frequency is irrelevant. It's
okay,
basically it's what they didn't do, and that you're trying to achieve at different frequencies, but you're trying to do it anyway. Yeah, so it's basically the same for the other comments that you have there. Okay, this, yeah, okay. On slide 6. It does not evaluate the need to use the full angular scan. 2 things. How do you define angular scan? And how do you come to understand? I think the question is, how do you come to understand that you actually needed to do that?
Okay, this is the first paper that we're using to compare. Is the same paper of the group. It's only a different frequency, and also what's here in evaporation. This is the same street that you use it. It's this one. This is the Nokia group was rated the same place we measured. The difference was the novelty. They don't evaluated the full angular scan. Here I call full angular scan is the beam steering. This is the case of beam steering that they'll analyze how if I can just point the antenna for a just fixed direction or use it in different direction.
Okay.
This was I want to explain how full angular scan.
Yeah, but it says does not evaluate the need to use the full angular scan. So you use it, but what is your analysis that says that you actually have to do that?
Yes, they did. don't in this work, in the end of this work, they scribe. We want to evaluate this full angular scan in 28, but it didn't do it. We did it in 60. There's the like the lack we have here, because this work is in the same environment, very similar equipment, the same group, only different is the frequency and this analysis actually.
Okay, so I guess the question should be: should you read that they just don't use the full angular scan in their analysis? Because my question was related to it says that the evaluation bit in that sentence.
Okay.
It means that you had to do some kind of analysis and then you evaluate it. Do I need to do this?
Yeah, because
where's that bit?
In the paper they say it.
No, you, because it's your work.
Yeah,
you're saying that they don't evaluate that.
Yeah, they don't.
So do you do that?
Yeah, I do it. I show it the base theory and fixed angular scan.
Okay.
Here. This is one.
Okay, can you go through this slide again, please?
Okay.
No, I mean,
what?
You was slide 28, I think.
28?
No, 27 is the last one.
Is it the slide of base theory you want to see?
Yes.
Okay.
Can you go through this slide again, please? Yeah, if you can.
Sure.
What I'm saying here.
In this case, what I want to analyze is what is better for my system, that I just fix the antenna one single direction, because we analyze all the angular spectrum for all the scenario that we have, and we saw the signal was really strange. All the power signal, the peak signal, is come from the alloy of the street. So what is better? Just put antenna there, points of the street, or analyze if you can just beam steering. You just put trying to put more antennas in different directions, and which is direction, what is the back's direction. So we saw that we have one maximum peak and second maximum peak, or third maximum peak, and we just mathematically use the difference from the max and the second best and the third best. And for a single direction, it's called the fixed direction, just points of the street. What is the penalty of this for the coverage? This is what I want to answer. And the penalty for just points the antenna for our first scenario is 7 dB. But if they use it, is turning around the street corner, the penalty is increased a little bit, 11. And if you just move the base station from the edge and just put there, and I don't know, maybe 10 meters of the edge, this has an offset. This is not it's not line of sight. How is the penalty? This is increasing even more, 60. Okay, so now not just point the antenna, choose best directions, and then just go decrease a little bit. If I shoot 3 directions, decrease even more. So in this case, if I use best direction, I've been steering for this all the environments. I have the maximum 13 dB for penalty. This was the evaluation they want to do in 28. They didn't, so I present here.
Okay. Now I understand. Thank you. Then if you go to slide 7. Thank you. 7. Then this is in the state of the art, they have limited angular sampling and idealized assumptions. What are those idealized assumptions?
Okay. In this case, they don't analyze like a fully angular scan. A lot of this work do not use the same.
Okay, but what is the assumption? They assume that.
They assume that they don't assume the directional gain degradation. They don't mention about this. This idealized assumption they have is only we have a model you can just characterize with this classical model, and this is it, this is the error, this is only the statistical way.
Okay, if you go to the next slide, in your goals it says to characterize and model the wireless channel in this indoor and outdoor environments to reliably predict the coverage and data rates.
Oh. Yes.
What is the data rate prediction?
Yeah, this is not supposed to be there. No, we don't use a data rate. We're not sending no one data. So not supposed to be there.
Okay. Okay. And okay. If you go to slide 13, yes, where you have all the models. Which one from all these models? Sorry, I think I need.
You have more than that.
Which one is? I mean, which ones from all of these are your models? Which ones are from references from the YouTube?
Okay, the reference we have here, the diffraction spire is the reference for 28.
Okay.
The single slope segment is also the reference for 28. They are made for the group,
okay.
proposed for the group. I propose this one. This is the knife edge base. And we already know the classic is slope intercepted. This is also already know. And I use it there, the cross reference factor, which is all okay. And also the group use it to reference azimuth gain.
Okay, so from your model, the proposed knife edge base model, if this is supposed to be a continuous function for the path gain, and you make x equal to dc in both equations, then L sub KED should be equal to 0.
So it was 0. But it's not 0, it was really small.
But if you look at the equations, you've got P1 plus 10n log 10x, then minus 0.0125 times x, I see.
Yeah, this is
and then minus LKED. So to have a continuous function, that should be equal to 0. So one is there. I don't get it.
Why is there?
If it's equal to 0 and you have two equations, but to make them equal at x equal to dc, then it should be 0.
Yeah, but this is a minus. This is a
no. But what I'm saying is, is that supposed to be a continuous function?
Yes.
Yes. Therefore, if you evaluate both equations at the same value, where both expressions meet, if you make a graph of that, they should have the same value.
They should have the same
Yes,
value.
to make it continuous. Otherwise, it will be discontinuous. The two curves should meet at one point. And that
Okay.
point should be D sub C.
Yeah. Okay.
If you compare both expressions, you've got P1 and P1. Just
Yeah.
yeah, 10 by 10. Then you have plus 10 times n times log 10 of x. Then at the end you have minus 0.0125x. Therefore, the only term that is the extra term is L sub KED. And if you make both equations as equal, when you evaluate x, when you make x equal to dc, then LKED should be 0. Therefore, you just have one expression. And I don't understand why you get this result.
Because we have analyzed when our antenna is not seeing the other user, and
Yes.
when our antenna is seeing, when he's seeing, when
Yes.
this is lost, we don't need the extra diffraction loss because it's not diffraction anymore.
But when I understand that, but when you evaluate both expressions at x equals to dc, you should get the same value. And the only way to get the same value is the LKED is equal to 0.
Okay.
So that's what I don't understand.
You don't understand why I have two equations.
No, but what I don't understand is that when you evaluate both equations, the only way to have both equations, to have them equal, so they give the same result, same number, that happens only when LKED is equal to 0.
Okay, it is.
So if it's 0, it just shouldn't be there. It's 0.
But
So you end up with just one
0
equation.
is only when this distance is it's not this one. When x, the distance x is only this when this distance is smaller than the distance that you have in
Yes,
x.
I understand that, but the question is, if let's say it's true,
Okay.
and if I evaluate both expressions when x is equal to dc, then I don't get the same
X
number.
equal to dc is only this equation because
But
we don't have diffraction when x
I
is equal
understand
to
that,
c.
but to make it a continuous function, it should be the same value at the very limit. Otherwise, it's not continuous. You will have a discontinuity. So, is it continuous or not?
For the say here okay, yes, you can see here. Okay, here we can see it has a continuity. It is, as you can explain the diagram. But in this case, I think, and as I process our data, we don't have access like DC. They never go like the equal because I'm not just using 1, 2, 3, 4 or arbitrary
Yes,
distance.
I understand that you have been something the space, like distance. But I don't have a problem with that. My question is that the path gain, if it is a continuous function, and if it is, then what you presented doesn't really match that description of a continuous function.
In this case, I think it's not. It's not supposed to be a continuous function because we have really we saw a break when we are seeing how it is any loss or restricted, and we saw when it didn't.
Okay.
So I think
So it's not.
It's not.
Okay.
Here. So.
Okay. Then slide 16.
16.
We've gone through this. But if you see, it's n is negative or positive. But you say that, in that table, it says that n is equal to -2. But then the note, it says that n could be true. So it's not clear.
Oh, no, I understand.
It's positive or
Because
negative.
in the free space, they don't use it -2. They use them 2 because this is path loss. So I just put here. If we know value for 2.
Yeah, I understand that. But you throughout the thesis, you're talking about path gain. Therefore, if you give any comments about what you're doing, it should also be related to path gain and not path loss.
Okay, this is only typo. As I say, it's only a
Yeah,
typo.
it looks like a typo
Yeah.
from that point of view, but it just yes, but also you have to be consistent throughout your manuscript. Yeah. Yeah, sure. Also from here, you mentioned which is actually just give me a second. Okay. There. This. There. Okay, so this expression, it's the path gain corridor to office, which looks very similar to the classical slow intercept.
It is.
It's basically the same, apart from the frequency factor. Two things. That frequency factor, you would get it. I mean, it's pretty standard.
The frequency factor, what?
The CFF. Because it's just 10 times the log of the, or 20 times the log of the frequency. Okay, so if you take Free's equation and you say I want to predict the received power, but I'll change the frequency, but I know what happens with this one, you get same factor. So from that point of view, it's not really a surprise. It's just what you will get because you use a different frequency. So in terms of prediction, I mean, the main difference is that you get a different intercept. That's it. The other term, the frequency factor, it comes naturally.
I understand. Okay.
And the other thing is that you have that X sigma, okay?
Okay.
And here it says that X sigma is it's Gaussian distributed, and then it represents the random deviation, and then it says root mean square error of the model. So is it the root mean square error of the model, or is it that Gaussian variable?
No, it's the Gaussian variable.
Okay, then why does it say it's the?
It's in the thesis, right?
Yes.
Yeah. I think it was like an error of that because it's supposed to be the standard deviation on this error.
Okay, good. That's the standard deviation. Okay, so when you consider the Gaussian variable and you consider the standard deviation and you put that to account for, the randomness of your system, you'll account for 86.6% or something like that, not 90%.
80% of what?
Yeah, because when you look at the Gaussian distribution, plus minus 1 standard deviation, that's about 66%.
Oh, okay.
So if you account for the 50%, which is the mean value, plus 1 standard deviation, you will account for half 50% plus 66.6 over 2. So that's 86%. That's not 90%.
Oh, I didn't realize this.
So that's why I was confused by your 90% when you put that number because if it's just that X sigma and you say that X sigma is actually the standard deviation, then that will be 86%, not 90%.
Oh.
Unless you mean something else by the 90%. I'm not sure if I understood everything you did. Right. I don't know if you can go to your thesis, page 13, because I'm not sure if these equations are in your presentation.
Well, which part?
Page 13. That's the number of the page.
13.
Yes. Oh, that's 11. So you have to go. Yeah.
This one.
Yes.
Okay.
Yeah. Okay. Can you explain this expression? It says that x1 is the distance from the transmitter to the corner and x2 from the corner to the receiver. So why would you have a distance between x1 and x2 if the receiver is at x2?
Here is the two corners. About one. X1 is your first corner, x2 or is 2, 3, 4 or whatever corners do you have.
Because it says x2.
Exactly.
The distance is from the transmitter to the corner and from the corner to the receiver.
Exactly. X1, while x1 are the distance from the transmitter to the corner and from the corner to the receiver.
So the receiver is at x2.
No. The D is the T along the path. Oh, yeah. Understand. Because here is the first, when it's lost, x1 from the receiver to the corner because it's lost. And x2 is the plus, where you have x1, x2 is after this corner.
Yes, but it says that x2 is where the receiver is located.
Yeah, exactly.
So,
but this is the same for the x1 because no, I understand what you said, and maybe here is not so good explain it because I use here x1 for a lot of the equations.
Yeah, but I mean that makes sense, but then it would be a function of. Yeah, because D is the
total.
Yeah, but it's like the straight line distance. And
I think maybe this is a good seeing in the presentation that I have x1 and x2.
Yeah, okay, if you have this in the presentation.
Yeah. It is, yeah. There it is, look, x1 and x2.
Yes, and it says that D would be between x1 and x1 plus x2.
The first?
Yes, but that will always be the case.
The second case is when I have the plus of this distance plus this one.
Yes, and that will always be the case because it's a triangle, so it's always the case. So that's why I don't understand why you would consider that the distance could be between x1 and x1 plus x2, considering that the receiver is at x2.
Do you think
it would be just a function of D. I mean,
it's the same. I think it's the same for the outdoor that you're saying. This up there, still there, up there, like and x until DC, x after DC.
Yes, it's something like that. Yeah, it is something like that. Yeah. Okay. Then. I have one question, which is, you have all your values in dB, but I was wondering if you computed everything in dBs, or do you do it in?
I do it pass.
Or was it adimensional and then?
We always pass to a dimension to dB.
Okay.
Because we have in power, and then you pass to dB.
Yeah, or adimensional units. Yeah, okay. Okay. If you go to slide 18. You mentioned that for the simulations you consider rise distribution for the envelope of the channel power. What did you assume for the K factor?
In indoor, when we process our data, we already have the value of key factor, but it didn't check it. We already have a key
You
factor
assumed
there.
a value
Yeah.
for that.
Yeah.
So would you, if you had a larger K factor, would you move the curve, the simulated curve to the right?
I think so. Maybe just a little bit. I don't remember actually.
So my question is, because you mentioned, I mean, that the idea was to compare the having an isotropic isotropic direction of arrival for all the multipaths. But if you had a larger K factor, then your simulations will be more similar to what you described as the azimuth game. So and also you mentioned that this is what you use to show your 90% of prediction. I also don't understand that 90% prediction again, because normally you consider that what you don't know or all the variations basically they behave like a random variable. If it's a log normal model, then in the logarithm scale you would consider a Gaussian variable, and then based on the standard deviation, assuming that's a zero mean variable, you would solve the interval to get the 90%, and that would be your let's say fading margin. That's how you kind of predict that 90%. Whereas, I mean, to get the 90% of coverage.
Yeah,
Whereas when you mentioned you want to predict that 90%, to get a reliable 90% prediction, it actually what you're saying is that from all your predictions, in 90% of the cases you'll get it correct, which is not the same.
Understand.
So that's why I have difficulties understanding why you did, because what you're saying is that your prediction, therefore, if you give me a frequency, you give me a distance, you give me a scenario, 90% of the time you'll get it right. That's what you're saying.
Okay.
So your title for me, more from signal processing and so on, is confusing.
Understand.
And if you mean that you want to ensure that the radio link, the availability will be 90%, then you have to get the standard deviation of your variations around your mean characteristic, and then you get the integral, and then yes, so yeah, like basically what you do with fading margins. But neither of those things are here, so that's why I have some difficulties understanding. I mean, I understand what you did, but the analysis and your conclusions they're not what I would expect from the title of your thesis. Yeah, so yeah, that's why I mentioned that 90%. I mean, I think that it requires a better explanation. I'm not saying that what you did is wrong. It's just that it's something different, or should be explained in a different way.
Understand.
Something like that.
Just work in this.
Yes, and the other thing is that when you you got your 90%, how in some of your comments on the tables, you mentioned the root mean square error, but it's not always clear what you use to compare that, because I mean you have your measurements and then you have your model, right?
My regression.
Yes, in order to say that you have some kind of error or you want some comparison, you either compare your model with another model, or you get new measurements and you compare the new measurements against all the models. So what do?
My regressions
are to validate models,
Okay,
you need
understand.
two sets
Okay.
of measurements of samples. One to get the model, the other one to validate.
Yeah.
When
I don't
but I didn't see that.
Yeah, no. Here
your
in
description,
in indoor, the only model that I used to like not compare, but to say that is the free space, because I don't compare nothing with nothing.
But then the root mean square error comes from.
The square error between my regression and my data.
But if you use the same, that's the thing that you're trying to. If you make that comparison that is not valid, to make it valid, you need another set of measurements, and then you compare your model to the new set of measurements. Or you just divide these into sets. That's it. You don't need, because you have a lot of measurements.
Really? This is a measure in the two different corridors. So the one we use to compare the other one in the one. Because we are doing for since a lot of time is only compare this error between our regression and our data. How is the dispersion of this line in our data? This is 2.5, 2.7.
Yes, but that, okay, so that shows that your model fits your measurements.
Yes.
Okay, but the question is, when you have a different environment, something very, very similar, let's say the next office.
Yeah, I understand.
How accurate will your model predict your new measurements?
Yeah, I understand.
If you say the root mean square error, it's basically the variance that you have.
Yeah, okay, I understand.
Or the certification that you have between your model from those points, from those measurements to the same measurements.
Let's see. Oh, here you can see I just used the two corridors and Persever and in Santa Maria. Yeah. So I use just for not to put and the results on the thesis, but only for the sanity check, as I say. I use the first, I make the regressions, calculate all the parameters in the corridor 1, you'll see.
Okay.
And then measure all the Casa Central, the Santa Maria, and use the same parameters to see if they match and they match. So okay, we can just put everything together.
You should.
Yeah, but it's only sanity check.
Yeah, no, but then you should say that. Actually, when you say root mean square error, that will be for the second set of measurements.
Oh, okay.
Because with the model, you're trying to get basically the value of n. Yeah. So so that's what you need from your model, and then the root mean square error is that. That's where you get the difference between your predictions, because that's what you're trying to say to predict.
We did the same in the outdoor.
Predict indoor. See, so your prediction. That's why you need to assess how good is your prediction from the model that you already have, and how good it is that you get that.
Here we did the same.
But if you don't mention that is from a different set of measurements, then there's no way I can understand that, because you mentioned that you have just a big number of measurements, but you don't say how you use those measurements.
I understand.
So
it's really a different way, point of view, because in the actually in our years of work, we just put it there and okay, this is a good match, is a small error, so it's fine. But here, yes, we did this for just a time check, and also did this in outdoor because we just used the parameters for one direction to predict the other direction is all the error.
Okay. Then if you go to slide 27.
27?
Yeah, that's when you have
the last one. Oh, was
yes.
it polemic?
Yes. This is basically your future work, right? So I have two questions. Why it looks like nothing is related to what you already did, Because if it's future work, it's somehow how you will continue your work from where you left it.
I understand.
And these are all different frequencies, even maybe a different problem. So I would expect, like, let's say, I'll try to do something.
Understand. No, maybe you can understand better when you know that in my graduation I worked and so 6 bands, and then in master I worked with 90, 115 with Laura with sensors, completely different, and then come back to 60, completely different. So for me it's not so hard to start something new, and actually for me it's more important what I'm doing to another person who can just give more time, because okay, you can just pass more 4 years working on this to put effort on this, or you can just ask for someone who is come for now, come here, and can just continue your work. For me, this is a good idea to continue, because okay, I can just keep doing this, searching more and more things to do, but then sometimes I will be only confined in this way. I really like to try something, things new.
Yeah,
I like it.
I understand, but traditionally when you talk about future work is something very related to what you've already done, like changes, a different scenario, or I don't know, different types of antenna, narrower beam, or whatever it is.
Other environments. So
yes, in general, it's either slight variation of what you've already done, or you focus on a particular application, or maybe you say, you know what, it's just the magnitude, I'll deal with the phase to get a whole picture of what the frequency response is, or whatever it is.
Okay. No, because also we have the limitation of the equipment, so I have to understand the limitation we have here, and I have to understand that I have chance to work with something new, and this will be good too. So for me,
no, I'm not saying that I think that this is so wrong. I don't think that. I'm just saying that the next step is the following step. So because you're saying that you're standing here and tomorrow you'll be back in Brazil. I mean, what I'm saying is that's why, or maybe, or in 5 seconds you'll be in Brazil.
This would be then be like a list of plans for a future career.
Yes, that's the thing. Yes, future work. Yes, it should be related to this. That's what I'm saying. The other thing is, why near field and sub-terahertz frequencies?
Oh, because this is study. We don't have this in the literature.
Okay, what would be the application for that?
There's has there we can just understand and use it just to a large bandwidth. All the system has a large bandwidth.
But it says near field. Near field for millimeter waves.
No. Millimeter, it is a near field for sub-terahertz waves, and this is 30 meters. This is the near field, and these antennas that are working 13 meters for the near field.
But you have
exactly.
It's millimeter waves, so near field would be right next to the antenna.
No.
Unless you have huge.
I have a huge, really directive antenna. So the distance for near fields is really far. Exactly. This is I want to work with this. We have all the measurement there, and I measure in a hallway with 29 meters, and it's still near field. And this is we want to analyze this. How this is so different that we want to expect it.
Okay.
It's not like this distance.
Can you tell the largest dimensions of the antenna?
Yeah, this is a lens antenna, has a A relay is 1.6 degrees of the half power bandwidth. So it's really directed. Is a 40 dBr of gain. 127 millimeters. Is it? Yeah, 127 is a circular one. I think a professor has a photo of this antennas and the presentation. 127 millimeters.
Sorry, this way you have it. Yeah. Yeah. That's the thing. That because so yeah, there's something that I would have to check because normally I'm sure you can understand why I'm sorry for the audience, but see the far field region will be to the square of lambda.
We just saw this too.
The dimensions of the antenna.
We analyzed all of this before we just start the measurement campaign. This is what we saw with this antenna, with this aperture and this gain. We just we can measure for above 13 meters.
Do you know the expression that relates the distance for the reactive near field or radiating near field?
Yeah, it's the same lambda d. Yeah.
But d is the dimension of the antenna.
Exactly.
So it's very small.
Yeah, but it's the dimension of antenna. It has a length of this antenna. So this is amplify the gain of the antenna. The gain of the antenna is 40 dB.
Yeah, but this expression doesn't mention the gain of the antenna, just the physical dimension.
I know.
That's why I'm asking you. You know,
yeah.
If you know the expression.
Yeah, I know. I know.
Are you sure?
No, it's not here. It's not here.
Yeah, I know that it's not here. So okay, anyway.
I understand what you say. This was the first thing that we calculated before starting the measurement.
Mm-hmm.
That's what I saw so interesting to see, because this antenna it has other students that already did this small distance, and she can prove, she validated, she has a paper on this, that the distance or near field with this antenna is smaller than is higher than we thought.
Okay, so how would you model an antenna with high gain antenna at sub-terahertz frequencies? You will need a huge anechoic chamber to do that, if that's the case.
They already did this. They already just.
So we couldn't do this yet because we don't have a 50-meter long.
Not here in Boston, they have.
Yeah, no, I'm talking about here in
Chile.
I don't know.
Yeah.
Probably
But the point of this is because I already have data, measuring data in two different environments, so I can process this and show a first draft of this data. This is one of my points. This one of this I don't have it, and with the equipment that we have, it's not so interesting because I need bandwidth. Our equipment is on narrow band, so I needed to send more information to this. Maybe with the equipment of Professor Rafael, it's okay to do. They have a really good VNA there, so maybe we can just work with this there. But in this case, for continuing, I have data in real environment, so this is the why I put there.
Okay. How would you? I mean, from your model, you can tell that there will be a path gain difference. Let's say if you're transmitting the carry set or the central frequency, it's 140 gigahertz. But if you move to, if you have a bandwidth of 2 gigahertz or so, there will be a slight difference in the path gain. From your expression, the 20 log of, remember?
Yeah.
What do you think that the receiver should do, or what kind of equipment should have the receiver to compensate for that difference?
For to compensate this.
Yeah, because you have 140 gigahertz,
Mhm.
that's what you're predicting, but at 139, the path gain will be different
Of course.
than the path gain at 141 if you have a 2 gigahertz bandwidth, which is what is intended to do at these frequencies. So what should the receiver, what kind of equipment or what should the receiver do to compensate for this difference?
Maybe they have to not use so much gain because they will compensate. I don't remember the word for this, but maybe they can just go down for the signal because our equipment has switch gains and they will use in some environments.
Yeah, but this is frequency dependent.
Yes.
So how will you do that?
I really don't think about this so specifically to this answer, but I think if we can just saw in mathematically way, we just only have to compensate the intercept that we're doing because the slope is the same. So we just have to, in some kind of way, but maybe get a signal more degraded. I don't think so. I don't think about this.
Okay. Basically, you can do it in two very basic ways. You can have a different gain of the amplifier at the transmitter when you know, from the different frequencies, not flat response. Or you just leave it to the equalizer to deal with whatever differences there are.
In this case, in the receiver,
Yeah,
not in the transmitter.
Yeah. If you want the transmitter to kind of fix this, then the frequency response of the amplifier, of the power amplifier, should not be flat. And if you don't want to deal with that and you want to, let the receiver do the job, you can expect the equalizer to fix all the differences. I can't remember if you mentioned here something about access losses or I read. Yeah. I can't remember if you read that or you mentioned that.
Access losses.
Yeah, that's what was the question. There, this enables the study of access losses. Second to last line. What are access losses?
Where?
Second to last line. Second to last. This enables the study of access losses. What are access losses? Second to last, if you go to the bottom line.
Yeah, I'm seeing this one too.
No, you go indoor, outdoor.
Oh.
Second to last. This enables the study of access losses.
I think this is only a way to say that I want to quantify again how much is the losses in this environment because we don't have it. This is maybe it's only a typo of to say because it's kind of the same. Losses is based on the losses, angular expression, and coverage. It's okay. In this way, we want to add these losses in this frequency because right now in the literature you have only outdoor measurement, only outdoor, and you have your losses there. But again, they don't analyze when you use it around a street corner. They will not analyze indoor office as using the same methodology that I use it. So this is, I think it's only a way to say the losses that I want to study, how can I quantify this one. Still do angular expressions and the coverage between indoor to outdoor, indoor to outdoor and outdoor to indoor.
Okay. And what was when you mentioned the measurements, you know, around the corner, going inside this office or whatever it was? What was the height of your transmitter you received?
The height.
The height.
Really good question. As we are using a narrow band, we don't. I don't calculate it just. But if I gonna use it wide band or the ultra wide band, this will be important to understand. In this frequency, for instance, 9, in this case, is volt 7 to 24, I think, dB.
No, I mean the height, the physical height where you installed the antenna that was spinning. What was the height of the transmitter?
Oh, the height of the antenna, okay, sorry. Was it 1.7 or 1.5?
Meters.
This was, meters.
Okay, so
from the ground.
They were not at the transmitter and the receiver, they were not at the same height.
No, the indoor, yes. The indoor was the same height, but the outdoor no, because outdoor we have it up at the building and the user. But the indoor, yes, they're 1.69 meters. Yes.
Okay.
Same height.
Okay, and then you mentioned the door.
Yeah,
that
the difference of the
it
door.
had some kind of little bits of glasses. What was the height of the glass? Where it was
the
located?
height of the glass was 4.12 meters, I guess, but it was.
Was a really high
really
door.
height. Yeah, all the buildings.
4 meters is probably more than this.
More than this. Yeah, exactly more than this, because all of this has all this office was like laboratory.
Yeah.
Some of the laboratory has really what is the name of this thing that you put? It was like a box that you have this. Is going from the ground to this is all the wall, a lot of boxes, so it's really high. 4.1, 3.9, but this is 4 is really high.
Okay, so basically the glass is actually the effect of the glass could be considered negligible because most of the wave would have to go through the door.
To the door, yes.
Okay. Yeah, because if it was a regular door, 2 meter door or something, then the glass would have some effect on the emissions. So that's what I was okay, so that's it. Thank you.
More leaders, so they. Thank you. Thank you so much.
Thanks to the examining committee for the question. And now I would like to give the word to Mauricio, who is the supervisor of Andreia.
What? Oh.
Yes, no question. Don't worry. No,
you can ask.
No, only I want to say.
I know you have a question.
Only I want to say thank you for all your work in the last 5 years. I know it was so difficult for you when you come here to Chile. You left your family. I know it's for the year with different difficulties for you, for the research, for the relationship between you and me. But that's I don't know why I speak all in English. Fue difícil, pero superaste todos los desafíos que te presentó tu doctorado. Así que te quería felicitar por todo el trabajo que hiciste, independiente del resultado y la nota que tengas. Así que pusiste todo tu empeño, toda tu energía en este trabajo durante 4 o 5 años. Así que muchas felicitaciones.
Okay, so now I'm going to ask the audience to leave the room so can the examining committee can deliver the final grade of Andreia. And in Spanish, por favor, esperen afuera. Hay un coffee break, cositas para comer. Y luego los vamos a llamar para que vengan a recibir la evaluación.
Sí, está todo listo.
Con micrófono, ¿no? Con micrófono, tiene que decirlo con micrófono. Ya. Muchas gracias nuevamente a la comisión examinadora, a la audiencia y por supuesto a Andreia por su presentación y las respuestas. Ahora voy a proceder a leer el acta. Ojo que voy a leer el acta, pero salió de la discusión de que hay revisiones menores sobre el documento que Andreia va a tener que solucionar, entregar el documento corregido para que esto se haga efectivo, ¿ya? Entonces, considerando la exposición del tema realizado por el alumno y su respuesta a las preguntas realizadas, cada integrante de la comisión calificó el examen en forma individual y secreta, promediando las evaluaciones, siendo la nota promedio de 6.2. En consecuencia, y considerando el reglamento del programa de doctorado actualmente vigente en la escuela, el promedio de nota de sus estudios y la obtenida en este examen, la dirección de la escuela enviará al señor decano expediente de grado en los siguientes términos. La Escuela de Ingeniería Eléctrica de la Facultad de Ingeniería de la Pontificia Universidad Católica de Valparaíso solicita al señor rector de la universidad se otorgue a Andreia Rodrigues López el grado de doctor en Ingeniería Eléctrica con la calificación final de 6,3, que corresponde a una nota conceptual de summa cum laude. Así que, muchas felicidades, pueden aplaudir. ¿Se puede saludar? Sí, pues.
Sí. Ahí va. 1, 2, 3. Otra. 1, 2, 3. Próxima. 1, 2, 3. Ya, ahora con. Ahí va. 1, 2, 3. Otra. 1, 2, 3. Próxima. 1, 2, 3. Ahora sí. No, estaba grabando y estaba sin sonido.
¿Voy a ir apurado más? No, ni. ¿Voy a acompañar a almorzar? Puede ser que no fuiste apurado, ¿no? Puede ser, pero
Déjame confirmar con la señora.
El grupo sigue mencionado. Foto con el grupo, con tus compañeros. Foto del grupo con los tíos.